The primary sources for Pythagorean philosophy come to us through Aristotle, who lived 2 centuries after Pythagoras and whose metaphysics contains crucial discussions of Pythagorean number theory. We have the biographical works of Iamblichus and Porphyry. Neoplatonic philosophers of the 3rd and 4th centuries CE, who composed elaborate lives of Pythagoras, drawing on earlier traditions. We have scattered references in Diogenes Laertius, whose lives and opinions of eminent philosophers preserves anecdotes and doctrines from the entire Greek philosophical tradition. We have fragments attributed to early Pythagoreans like Philolaus and Archytas, though even these texts present difficulties of authenticity and interpretation. What this means is that any account of Pythagorean philosophy must navigate carefully between documented fact and accumulated legend, between verifiable mathematical discoveries and mystical doctrines whose origins remain uncertain. We must speak simultaneously of what Pythagoras and his followers actually taught, insofar as we can determine it, and of the powerful myth of Pythagoras that took shape in later antiquity and that itself became a force in Western intellectual history. Pythagoras was born around 570 BCE on Samos, a prosperous island known for its advanced engineering, maritime trade, and cultural sophistication. The island was ruled during Pythagoras' youth by the tyrant Polycrates, whose court attracted poets, artists, and intellectuals from across the Greek world. Ancient sources tell us that Pythagoras studied with Pherecydes of Syros, an early cosmological thinker, and with Thales and Anaximander, the great Milesian philosophers who had begun the project of explaining natural phenomena through rational principles rather than mythological narratives. Whether these specific teacher-student relationships are historical or represent later attempts to locate Pythagoras within a philosophical lineage, they point to a genuine intellectual context. The Ionian coast in the 6th century was alive with new forms of inquiry, with attempts to understand the cosmos through observation, reason, and the search for underlying principles of unity and order. The biographical tradition emphasizes Pythagoras' extensive travels beyond the Greek world. Sources describe journeys to Egypt, where he supposedly studied with priests and learned geometry and astronomical law. Some accounts place him in Babylon, absorbing Chaldean wisdom and mathematical techniques. Still others send him to Persia to encounter the teachings of Zoroaster, or to Crete to study the laws of Minos. Modern scholarship treats these travel narratives with skepticism, recognizing them as common tropes in ancient biography, ways of explaining how a sage acquired his wisdom by contact with venerable foreign traditions. Yet even if the specific journeys are legendary, they reflect something significant. Pythagorean philosophy did incorporate mathematical knowledge from Egypt and Babylon, astronomical observations from Mesopotamia, and religious ideas about the soul that may have had Eastern precedents. The travel narratives, whatever their historical basis, acknowledge that Pythagoras, or his school, integrated diverse cultural and intellectual traditions into a distinctive Greek philosophical synthesis. Around 530 BCE, according to ancient accounts, Pythagoras left Samos and settled in Croton, a prosperous Greek city in southern Italy. The reasons for his departure remain uncertain. Some sources suggest he fled the tyranny of Polycrates. Others describe him seeking a location more conducive to establishing a philosophical school. Still others frame his migration in quasi-religious terms, as a divinely ordained mission. What is historically clear is that Croton became the center of Pythagorean activity, and that the movement Pythagoras founded there differed fundamentally from other philosophical schools of the period. This was not merely an informal circle of students gathered around a teacher, as with the Milesian philosophers. Nor was it a public school of rhetoric and debate, as the sophists would later establish. The Pythagorean community at Croton was something unprecedented, a tightly organized religious and philosophical society with strict rules of conduct, communal property, hierarchical initiation, and doctrines kept secret from outsiders. The community attracted followers from Croton's elite families and from other cities in Magna Graecia. Ancient sources describe Pythagoras as a charismatic teacher whose lectures drew large crowds, including women, which was unusual for the period. The biographical tradition presents him as a figure of almost superhuman wisdom and virtue, capable of miraculous feats, predicting earthquakes, calming storms, appearing in two places simultaneously, remembering past incarnations of his soul. These legendary elements, clearly products of later hagiography, nevertheless point to the extraordinary reverence in which Pythagoras was held by his followers. He was not simply a philosopher in the later academic sense. He was the founder of a way of life, a guide to salvation, a figure whose authority derived not only from rational argument, but from spiritual insight and personal sanctity. The Pythagorean school at Croton functioned simultaneously as a philosophical academy, a religious community, and a political faction. Members lived according to strict regulations governing diet, dress, speech, and daily routine. They held property in common and addressed one another as brothers and sisters. They observed periods of silence and engaged in regular practices of self-examination and purification. The inner circle of students, having passed through stages of initiation, received direct instruction in the mathematical and philosophical doctrines. The outer circle participated in the communal life and ethical teachings without access to the school's deeper secrets. This hierarchical structure, with its emphasis on gradual revelation of truth to properly prepared students, would influence later philosophical and religious movements throughout antiquity and beyond. The doctrines taught within the Pythagorean community centered on a radical claim: that number is the fundamental reality underlying all things. This assertion, which seems strange and abstract to modern readers, represented a revolutionary philosophical breakthrough. Earlier Greek thinkers had sought the basic substance of reality in material elements like water, air, or fire. The Pythagoreans proposed instead that reality is fundamentally structural and relational, that the essence of things lies not in what they are made of, but in the mathematical relationships that give them form and order. This insight opened philosophy to a new domain of inquiry, one that would prove extraordinarily fertile for the development of mathematics, natural science, and metaphysics. It suggested that the cosmos is intelligible, that human reason can grasp its underlying principles, and that these principles are expressible in precise quantitative terms. The Pythagorean focus on number arose from concrete mathematical and musical discoveries. The school made fundamental contributions to geometry, including the famous theorem relating the sides of a right triangle. They investigated the properties of triangular, square, and other figurate numbers. They discovered that musical consonances correspond to simple numerical ratios: an octave to 2 to 1, a perfect fifth to 3 to 2, a perfect fourth to 4 to 3. These discoveries revealed an astonishing fact: qualities of experience that seem purely subjective, like the beauty of musical harmony, actually depend on precise quantitative relationships. The cosmos, it appeared, operates according to mathematical laws. Harmony, proportion, and order are not human constructions imposed on a chaotic world, but objective features of reality itself, graspable through number. This mathematical approach to reality carried profound religious and ethical implications for the Pythagoreans. If the cosmos is ordered by number, then understanding these numerical principles becomes a path to wisdom and virtue. The study of mathematics purifies the soul by turning it toward eternal truths rather than transient sensory experiences. The practice of music attunes the soul to cosmic harmony. The cultivation of proportionate relationships in one's own life, adhering to measure and balance in all things, aligns one with the fundamental structure of reality. Philosophy becomes not merely intellectual inquiry, but spiritual discipline, a way of preparing the soul for its ultimate destiny. For the Pythagoreans believed in the immortality and transmigration of the soul, in its journey through successive incarnations, and in the possibility of liberation from this cycle through philosophical and ethical purification. The early success of the Pythagorean movement in Croton and neighbouring cities brought it into conflict with democratic factions and rival elite groups. The Pythagoreans, drawn largely from aristocratic families and advocating oligarchic political principles, became targets of populist resentment and political violence. Around 500 BCE, according to ancient accounts, anti-Pythagorean riots erupted in Croton and other cities where the school had established communities. Meeting houses were burned, members were killed, and the survivors scattered throughout the Greek world. Pythagoras himself, accounts vary, either died in the violence or fled to Metapontum, where he died shortly thereafter. The details remain uncertain, but the persecution was real, and it marked a crucial turning point. The unified community centered on the living presence of its founder gave way to a dispersed network of followers who carried Pythagorean teachings to Athens, mainland Greece, and beyond. Yet the suppression of the organized Pythagorean communities did not end the influence of Pythagorean ideas. Throughout the 5th and 4th centuries BCE, Pythagorean doctrines continued to circulate, adapted and developed by philosopher-scientists like Philolaus, Archytas, and Hippasus. Pythagorean concepts profoundly influenced Plato, whose academy in Athens became a center for mathematical philosophy. Plato's theory of forms owes much to Pythagorean ideas about eternal mathematical realities underlying the changing sensible world. His cosmic vision in the Timaeus draws extensively on Pythagorean cosmology and number theory. Aristotle, though critical of Pythagorean metaphysics, preserved detailed accounts of their doctrines in his works, ensuring that later generations would have access to these teachings. In the Hellenistic period and late antiquity, Neo-Pythagorean movements revived interest in Pythagoras as a sage and wonder worker, blending authentic early doctrines with later philosophical and religious developments. The figure of Pythagoras thus bridges multiple domains: mathematics and mysticism, reason and revelation, scientific inquiry, and religious practice. He represents a vision of philosophy as comprehensive wisdom, embracing not only theoretical understanding, but practical ethics and spiritual transformation. The Pythagorean way of life integrated intellectual pursuit with moral discipline, mathematical study with musical practice, cosmological theory with religious ritual. This integration, however we assess its viability or coherence, reflects an understanding of philosophy that would persist through much of ancient and medieval thought. The idea that true knowledge transforms the knower, that understanding the cosmos means aligning oneself with its order, that reason and virtue are inseparable. To study Pythagorean philosophy is to encounter the foundations of Western mathematics and the origins of a mathematical approach to natural science. It is to trace the emergence of the concept of proof, of deductive reasoning from first principles, of systematic theoretical knowledge. It is to see the birth of a metaphysics grounded in structure and relation rather than substance and matter. But it is also to confront questions about the limits of mathematical explanation, about whether quantities exhaust reality or merely describe one aspect of it, about whether the discovery of mathematical order in nature implies that nature is exhaustively mathematical. The Pythagoreans made claims that remain philosophically live, that mathematics reveals truths about reality, not just useful fictions or conventional descriptions, that the universe exhibits rational order accessible to human understanding, That knowledge of this order has ethical and spiritual significance. The historical distance separating us from Pythagoras, the fragmentary nature of the evidence, the layers of legend obscuring the facts, none of this diminishes the philosophical interest of Pythagorean thought. Indeed, the very difficulties of historical reconstruction remind us that philosophy is not simply a record of what past thinkers said, but an ongoing engagement with perennial questions. When we ask what Pythagoras taught about number, we are also asking what mathematics is and how it relates to reality. When we examine Pythagorean cosmology, we are exploring our own assumptions about order, beauty, and intelligibility in nature. When we consider the Pythagorean way of life, we are reflecting on the relationship between knowledge and virtue, between understanding and transformation. The Pythagoreans created a philosophical tradition that has continuously renewed itself across 25 centuries, precisely because it addresses questions that every age must confront anew. In the chapters that follow, we will examine the doctrines and practices of the Pythagorean school in detail. We will explore the communal life established at Croton, with its rules and rituals, its ethical teachings and hierarchical structure. We will analyze the central claim that all is number, attempting to understand what the Pythagoreans meant by this doctrine and how they justified it. We will investigate the sacred symbol of the Tetractys, the triangular arrangement of the first four numbers that embodied fundamental cosmological principles. We will trace the mathematical discoveries of the Pythagorean school, from geometric theorems to the recognition of irrational magnitudes. We will examine the theory of musical harmony and its extension to a cosmic harmony, the music of the spheres. We will consider Pythagorean teachings about the soul, its immortality, its transmigrations, and its purification. We will assess the ethical and political dimensions of Pythagoreanism, and finally, we will survey the immense legacy of Pythagorean thought in Platonism, medieval cosmology, Renaissance philosophy, and modern mathematics and science. Each topic presents its own challenges of evidence and interpretation. Each requires us to distinguish, where possible, between early Pythagorean doctrines and later developments, between mathematical results and mystical elaborations, between what can be responsibly affirmed on historical grounds and what remains speculation. Yet through this careful examination, a coherent philosophical vision emerges, a vision of reality as fundamentally intelligible, structured by mathematical relationships, exhibiting order and beauty, and accessible to human understanding through disciplined inquiry and contemplative practice. Whether we ultimately accept this vision or not, engaging with it enriches our understanding of philosophy itself, of its possibilities and perennial questions, of the enduring human aspiration to comprehend the nature of reality and our place within it. The philosophical school established by Pythagoras at Croton was not merely an institution for teaching doctrines or conducting research, it was a comprehensive way of life, a community bound by shared beliefs, practices, and loyalties that permeated every aspect of daily existence. To join the Pythagorean brotherhood was to accept a rigorous discipline encompassing diet, speech, conduct, study, and spiritual practice. This all-encompassing structure distinguished the Pythagorean movement from other philosophical schools of antiquity and gave it a quasi-religious character that would influence later philosophical and spiritual communities throughout Western history. Understanding Pythagorean philosophy requires understanding this way of life, for the doctrines were never conceived as abstract theories divorced from practice, but as principles to be lived, embodied, and enacted within a community dedicated to wisdom and virtue. The biographical sources, particularly Iamblichus and Porphyry, provide detailed accounts of the organization and daily practices of the Pythagorean community. While these late sources certainly contain embellishments and may project later Neo-Pythagorean practices, back onto the early movement. They preserve authentic traditions about the school's structure. The community was hierarchically organized, with a clear distinction between the inner circle of initiates, called the mathematikoi, or learners, and the outer circle, called the akousmatikoi, or listeners. The mathematikoi lived in close association with Pythagoras, received direct instruction in the philosophical and mathematical doctrines, held property in common, and participated fully in the school's esoteric teachings. The akousmatikoi attended lectures, observed the ethical rules, and participated in the communal life, but did not have access to the more advanced teachings. This distinction reflects a pedagogical principle, that truth must be revealed gradually to students as they become capable of understanding it, and that premature exposure to complex doctrines could lead to confusion or misuse. Entry into the Pythagorean community required a careful process of evaluation and preparation. According to ancient accounts, Pythagoras did not accept students immediately, but observed them over time to assess their character, temperament, and suitability for the philosophical life. Candidates were evaluated on their capacity for self-control, their motivation for seeking wisdom, their relationships with family and friends, their reactions to praise and criticism. This emphasis on character assessment reflects the Pythagorean conviction that philosophy is not purely intellectual but involves moral transformation, and that not everyone is prepared for or capable of this transformation. Only those who demonstrated appropriate qualities were admitted as students, and even then, they entered into a probationary period during which their commitment and progress were tested. Once admitted, new students underwent an initial period of silence lasting several years. This practice of imposed silence, which seems harsh to modern sensibilities, served multiple pedagogical and spiritual functions. It cultivated attentiveness and receptivity, training students to listen carefully rather than speaking hastily. It disciplined the mind by restraining the constant impulse to verbalize thoughts and reactions. It created a contemplative atmosphere conducive to absorbing the teachings. It also served as a test of commitment and obedience, demonstrating that the student was willing to submit to the discipline of the school. During this period of silence, students attended lectures and participated in communal activities, but were not permitted to ask questions or engage in philosophical discussion. They observed, listened, memorized, and reflected, internalizing the teachings before being allowed to examine them critically. After successfully completing this probationary period, students were initiated as mathematikoi and gained access to the school's esoteric doctrines. They could now engage in dialectical inquiry, pose questions, and participate in the collective investigation of philosophical and mathematical problems. They shared fully in the communal property of the school, surrendering their personal possessions to the common treasury. This practice of communal ownership served both practical and symbolic purposes. Practically, it ensured that all members had their material needs met and could dedicate themselves fully to study without financial concerns. Symbolically, it enacted the principle of friendship and unity that the Pythagoreans regarded as fundamental to the philosophical life. The saying attributed to Pythagoras, that friends hold all things in common, expressed not just a social ideal, but a metaphysical truth about the unity underlying apparent multiplicity. The daily routine of the Pythagorean community followed a structured pattern designed to cultivate philosophical virtue and insight. Members rose at dawn and began the day with solitary contemplation, reviewing the studies and reflections of previous days and preparing the mind for new learning. This was followed by a walk, preferably in a natural setting, as movement and observation of nature were considered conducive to thought. The morning was devoted to study and instruction, with lectures by Pythagoras or advanced students on mathematical, philosophical, and ethical topics. The middle of the day involved physical exercise, as the Pythagoreans held that a healthy body supports a healthy soul, and that regular exercise contributes to both physical and mental discipline. The afternoon brought communal meals, conversation about the day's teachings, and collaborative study. The evening concluded with self-examination as members reviewed their actions and thoughts, identifying failures to live up to Pythagorean principles and resolving to do better the following day. This practice of daily self-examination, which would be adopted by later philosophical schools including the Stoics, reflects the Pythagorean emphasis on philosophy as transformative practice rather than merely accumulation of knowledge. 3 questions were to be asked each evening. What have I done wrong? What have I accomplished? What duties have I left unfulfilled? This systematic review of conduct cultivated moral awareness and intentionality, training practitioners to bring their lives progressively into alignment with rational principles. The goal was not perfection, which no human could achieve, but constant improvement, a gradual purification of the soul through attentive practice and self-correction. Philosophy was understood as a discipline analogous to medicine. Just as the physician heals the body through careful diagnosis and treatment, so the philosopher heals the soul through examination and practice. The ethical teachings of the Pythagorean school emphasized self-control, moderation, and justice. Self-control, particularly over bodily appetites and emotional reactions, was considered fundamental to philosophy. A person enslaved to desires and impulses cannot think clearly or act virtuously. Cultivating self-control through regular practice, through habituation to rational principles, liberates the soul from domination by irrational forces and enables it to direct itself according to reason. Moderation, the principle of measure and balance, extended this basic insight. In all things, excess was to be avoided. Even virtues pursued immoderately could become vices. The goal was harmony, proportion, the fitting response appropriate to each situation. This ideal of moderation connected directly to the Pythagorean mathematical vision. Just as musical harmony depends on the right proportions, so ethical virtue depends on the right balance of qualities in the soul. Justice for the Pythagoreans was understood fundamentally as reciprocal equality, as rendering to each what is due. This conception, which would influence Plato and Aristotle, treated justice as a kind of mathematical proportion. In exchanges between persons, justice requires equality of contribution and return. In the distribution of goods, justice requires that shares be proportionate to merit or need. In punishment of crimes, justice requires that penalty be proportionate to offence. This mathematical conception of justice reflected the broader Pythagorean commitment to proportion and measure as fundamental features of reality. Just as the cosmos exhibits mathematical order, so human social relations should exhibit proportionate structure. To act justly is to instantiate cosmic order in the human realm, to align one's conduct with the rational structure that pervades all things. Friendship occupied a central place in Pythagorean ethics and community life. The Pythagoreans regarded friendship as the highest human relationship, the perfection of social life. True friendship, they held, is based on similarity of character and shared pursuit of wisdom and virtue. It requires complete honesty, mutual trust, and willingness to sacrifice personal interest for the friend's good. The ideal of friendship shaped the structure of the Pythagorean community, which was conceived as a brotherhood of friends dedicated to common goals. Members addressed one another as brothers and sisters, shared property and resources, supported one another in difficulty, and regarded the good of the community as inseparable from their individual good. This emphasis on friendship as philosophical ideal would influence Plato's Republic and Aristotle's extensive analysis of philia in the Nicomachean Ethics. The Pythagorean community was notable for including women as members and students, unusual in a society where women were typically excluded from formal education and public intellectual life. Ancient sources mention several prominent female Pythagoreans, including Theano, identified in some accounts as the wife of Pythagoras and a philosopher in her own right. Whether women participated fully in all aspects of the school's activities or occupied a somewhat separate sphere remains unclear from the fragmentary evidence. What seems certain is that Pythagorean philosophy recognized women as capable of philosophical education and attainment of wisdom, even if the practical arrangements may have reflected broader social constraints. This relative openness to female participation distinguished the Pythagoreans from many other philosophical schools and contributed to the movement's appeal. Dietary restrictions played a significant role in Pythagorean practice, though the precise nature and rationale of these restrictions present interpretive difficulties. Ancient sources agree that Pythagoreans abstained from eating meat, but the reasons given vary. Some sources emphasize the doctrine of metempsychosis. Since the soul can transmigrate into animal bodies, to eat animal flesh is potentially to consume one who was or could be a human being, perhaps even a friend or relative. Other sources stress the connection between diet and spiritual purification. A simple plant-based diet keeps the body pure and the mind clear, facilitating philosophical contemplation. Still other sources suggest medical or ethical considerations, that meat-eating inflames the passions, promotes aggression, and departs from the natural human diet. Modern scholarship debates whether the prohibition on meat was absolute from the beginning or whether it developed over time and whether it applied to all members or only to the inner circle. Particularly controversial is the tradition regarding beans. Many ancient sources report that Pythagoreans refused to eat beans, and some elaborate accounts explain this prohibition in mystical terms. That beans contain souls, or that they symbolize the process of generation, or that they are connected to the realm of the dead. Other sources treat the bean taboo as allegorical or as reflecting practical medical concerns about flatulence and digestive disturbance. Still others suggest the prohibition applied to participation in democratic voting procedures, which used beans as tokens, rather than to consumption of the legume itself. Whatever the original basis of the dietary rules, they functioned within the community as markers of identity and commitment. To observe these restrictions was to enact Pythagorean principles, to distinguish oneself from ordinary society, and to maintain the purity required for philosophical and spiritual progress. Clothing and personal appearance were also regulated in the Pythagorean community. Members wore simple white garments made of linen, avoiding luxury fabrics and ostentatious display. White symbolized purity and dedication to philosophy. Linen was preferred over wool because it came from plants rather than animals. Hair and beard were kept in moderate fashion, neither elaborately styled nor completely neglected. The goal in all aspects of appearance was simplicity and moderation, avoiding both the vanity of excessive attention to appearance and the affectation of deliberately slovenly presentation. Physical appearance, like all aspects of life, should reflect rational order and proportion. Music and mathematical study formed core components of daily practice. Music was not merely entertainment, but a spiritual and philosophical discipline. The Pythagoreans practiced singing and playing instruments, particularly the lyre, both for the intrinsic pleasure and beauty of music and for its effects on the soul. They believed that music could calm passions, induce appropriate emotional states, and attune the soul to cosmic harmony. Different musical modes were thought to have different ethical and psychological effects, and skilled musicians could use these effects therapeutically. Mathematical study, the investigation of number and geometric form, was considered the highest intellectual activity, one that turns the mind from sensible particulars to eternal truths and prepares the soul for ultimate liberation. The Pythagorean community maintained strict secrecy about its doctrines, particularly the more advanced mathematical and metaphysical teachings. Members were bound by oath not to reveal these teachings to outsiders. This secrecy served multiple purposes. It protected the school's intellectual property in an era when philosophical teachings were sometimes regarded as trade secrets. It maintained the hierarchical structure by ensuring that advanced doctrines were available only to properly initiated members. It created an aura of mystery that enhanced the school's prestige and appeal. It also reflected the conviction that profound truths cannot simply be transmitted through words, but require preparation, practice, and direct insight. To reveal advanced doctrines to the unprepared would be both futile and dangerous. Futile because the unprepared could not understand them, dangerous because partial or distorted understanding might lead to error or misuse. Various legends and anecdotes illustrate the importance of secrecy in Pythagorean tradition. The most famous concerns Hippasus of Metapontum, a member of the school who supposedly revealed either the existence of irrational numbers or the construction of the dodecahedron, both of which were kept secret. According to different versions of the story, Hippasus was expelled from the community, or died in a shipwreck as divine punishment, or was symbolically buried by his fellow Pythagoreans to signify his death to the philosophical life. Whether or not these dramatic accounts have historical basis, they express the community's serious commitment to preserving its doctrines within the initiated circle. The Pythagoreans developed a distinctive way of teaching that combined direct instruction with symbolic sayings and oral transmission. These symbolic sayings, called akousmata, or things heard, were brief prescriptive statements, often enigmatic or paradoxical in form. Examples include: abstain from beans, do not step over a crossbar, do not stir the fire with iron, do not eat from a whole loaf. Some of these sayings had literal application as rules of conduct. Others functioned as memory devices or meditation topics, concealing deeper philosophical meanings that teachers would explain to advanced students. Still others may have been practical advice presented in memorable form. This method of teaching through pithy sayings required active engagement from students, who had to reflect on the meanings, ask questions, and discover truths for themselves rather than passively receiving information. Religious practice permeated Pythagorean community life, though the relationship between the philosophical and religious dimensions of Pythagoreanism presents interpretive challenges. The Pythagoreans honoured the traditional Greek gods and participated in civic religious observances. They also developed distinctive rituals and practices reflecting their own doctrines. They engaged in purification rites, both physical and spiritual. They practiced forms of prayer and meditation. They observed particular days as sacred and others as inauspicious. They consulted oracles and practiced divination. Some sources suggest they regarded Pythagoras himself as more than human, perhaps as an incarnation of Apollo or another divine being. This religious dimension raises questions about the relationship between Pythagorean philosophy and Greek mystery religions, and about whether Pythagoreanism is best understood as a philosophical school, a religious cult, or some hybrid form. The tension between reason and revelation, between philosophical inquiry and religious authority, characterized Pythagoreanism from its origins. On the one hand, the school made fundamental contributions to mathematics and sought rational understanding of natural phenomena. The doctrine that all is number represented an attempt to explain reality through intelligible principles accessible to reason. The emphasis on proof and demonstration in mathematics reflected commitment to rational justification. On the other hand, Pythagoras was regarded not merely as a brilliant thinker, but as a sage possessing supernatural insight. His teachings were transmitted as authoritative doctrines rather than as hypotheses open to revision. The phrase itself, he said, autos epha, became a mark of Pythagorean teaching. Authority derived from the founder's word rather than from independent argument. This combination of rational inquiry with reverence for authority would recur throughout the history of philosophy. Aristotle's criticisms of the Pythagoreans often target precisely this blending of mathematics with mysticism, reason with authority. He acknowledges their mathematical achievements, but questions their metaphysical claim that things are numbers rather than merely being describable by numbers. He recognizes their insights into proportion and harmony, but objects to their extension of these concepts beyond legitimate application. For Aristotle, the Pythagoreans represent both the promise and the peril of mathematical philosophy. Promise in their recognition that mathematics can illuminate natural phenomena, peril in their tendency to treat mathematical relations as exhaustive of reality. This tension between mathematical explanation and mathematical mysticism runs through the entire Pythagorean tradition and emerges in different forms at different historical moments. The eventual suppression of the Pythagorean communities in southern Italy did not end the influence of Pythagorean ideas and practices. Scattered members continued to teach and write, adapting Pythagorean doctrines to new contexts. Pythagorean ethical teachings about self-examination, friendship, and the philosophical life influenced later schools, particularly Stoicism. Pythagorean dietary practices found echoes in various ascetic and vegetarian movements. The ideal of a philosophical community living according to shared principles inspired numerous later attempts, from Plato's academy to monastic communities to modern intentional communities. The integration of mathematical study with ethical and spiritual practice established a model that would recur in later philosophical and religious traditions. The Pythagorean way of life embodied a comprehensive philosophical vision, that reality has an intelligible structure, that human beings can grasp this structure through reason and study, that understanding this structure has ethical implications, and that living according to rational principles leads to happiness and spiritual fulfillment. This vision required not just intellectual assent, but practical commitment, not just learning doctrines, but transforming one's entire existence. The community structure, with its rules and practices, its disciplines and aspirations, provided a framework for this transformation. To be a Pythagorean was not simply to hold certain beliefs, but to live a certain kind of life, oriented toward wisdom, virtue, and the ultimate good of the soul. The Pythagorean doctrine of number did not arise from purely abstract speculation, but emerged from concrete observations about the mathematical structure of reality. The school's fundamental insight was that many apparently qualitative features of experience, features that seem to depend on subjective perception or to lack any objective basis, actually correspond to precise quantitative relationships. The most striking example was the discovery that musical harmony depends on numerical ratios. When a string is divided in the ratio 2:1, the two parts produce notes an octave apart. When divided 3:2, they produce a perfect fifth. When divided 4:3, they produce a perfect fourth. These simple ratios of 1 through 4, the numbers of the sacred Tetractys, generate the fundamental consonances of Greek music. This discovery was revolutionary. It demonstrated that aesthetic experience, which might seem purely subjective, has an objective mathematical foundation. The beauty of musical harmony is not merely in the ear of the listener, but reflects actual quantitative relationships in the sound-producing objects. Moreover, these relationships are not arbitrary, but form patterns that the mind can grasp and systematize. This suggested a stunning possibility that other domains of experience might similarly rest on mathematical foundations, that beneath the apparently chaotic flux of sensory qualities lie stable numerical relationships, and that reality itself might be fundamentally mathematical in nature. The Pythagoreans extended this insight beyond music to other domains. They observed that physical objects have definite shapes and sizes, which can be analysed geometrically and measured numerically. They noted that motions occur at definite rates and over definite distances, describable in mathematical terms. They recognised patterns and regularities in natural phenomena, the alternation of day and night, the phases of the moon, the cycle of seasons, all of which exhibit periodic regularity expressible in numbers. They studied the properties of particular numbers, finding patterns in square numbers, triangular numbers, and other figurate numbers. They investigated ratios and proportions, recognizing that the same mathematical relationships appear in diverse contexts. All of this contributed to the conviction that number is not merely a tool for describing reality, but constitutes reality's essential nature. Aristotle's account of Pythagorean number theory in the Metaphysics emphasizes that the Pythagoreans regarded numbers as the material constituents of things. They held that sensible bodies are composed of numbers in somewhat the way that other thinkers held they are composed of fire, water, earth, and air. This interpretation raises immediate difficulties. Numbers are abstract entities, or so it seems, lacking location, shape, and causal powers. How could physical objects literally be made of numbers? How could something abstract compose something concrete? Aristotle himself regarded this aspect of Pythagorean doctrine as confused, a failure to distinguish between the properties things have and the things themselves, between mathematical descriptions of reality and reality's intrinsic nature. Yet perhaps the Pythagorean position was more subtle than Aristotle's critique suggests. Rather than claiming that physical objects are numerals, or that we could encounter the number 3 sitting on a table, the Pythagoreans may have been proposing that reality's fundamental nature is structural and relational rather than substantial and material. What makes something the kind of thing it is, what accounts for its properties and behaviours, is not some underlying material stuff, but the pattern of relationships it exhibits. A triangle is what it is not because of what it is made of, but because of the relationships among its parts. 3 vertices connected by 3 straight lines, interior angles summing to 2 right angles, and so forth. This structural identity holds regardless of whether the triangle is drawn in sand, constructed from wooden sticks, or merely contemplated in thought. If this interpretation is correct, the Pythagorean doctrine anticipates modern scientific approaches that analyze phenomena in terms of structures, patterns, and mathematical relationships rather than in terms of substances and qualities. Contemporary physics describes particles not primarily by intrinsic properties, but by how they interact according to mathematical laws. It represents fields through differential equations and symmetries through group theory. It models reality using abstract mathematical structures whose connection to everyday experience is often highly indirect. The Pythagorean claim that reality is number, understood as the claim that reality is fundamentally structural and mathematical, does not seem quite so strange from this perspective. It appears instead as an early, philosophically informed version of the basic assumption underlying mathematical physics. The Pythagorean association of numbers with particular qualities and entities reflects another dimension of their number philosophy. They held that odd numbers were male and even numbers female, that 1 represented reason, 2 opinion, 3 harmony, 4 justice, 5 marriage, and so forth. They associated numbers with geometric shapes, 1 with the point, 2 with the line, 3 with the plane, 4 with the solid. They regarded certain numbers as particularly significant, 10 as the perfect number containing the others, 7 as associated with various natural phenomena, 8 as the first cube. Modern readers often dismiss these associations as arbitrary or fanciful, but they reflect serious attempts to discern meaningful patterns and correspondences. These numerical associations operated at multiple levels. At a basic level, they functioned as memory devices and teaching tools, helping students remember philosophical doctrines by linking them to numbers. At a deeper level, they expressed genuine insights about structure. Consider the association of 1 with the point, 2 with the line, 3 with the plane, and 4 with the solid. This sequence represents increasing dimensions of geometric space, a real and mathematically significant pattern. Or consider the idea that 5 represents marriage. 5 is the sum of the first even and odd numbers after 1, symbolizing the union of male and female. While the gendering of even and odd numbers reflects cultural assumptions we would not endorse, the mathematical relationship 5 equals 2 plus 3 remains valid, and recognizing such relationships among numbers constitutes legitimate mathematical investigation. The difficulty lies in distinguishing between mathematically grounded associations and purely speculative ones, between recognizing real structural patterns and imposing arbitrary symbolic meanings. The Pythagoreans themselves may not have always maintained this distinction clearly, particularly in later developments of the tradition, when numerological speculations sometimes overwhelmed mathematical rigor. Yet the basic impulse to find meaning in mathematical relationships, to see in numerical patterns reflections of cosmic order, has repeatedly recurred in intellectual history, from Kepler's search for mathematical harmonies in planetary motions to contemporary attempts to find mathematical beauty in fundamental physical laws. Aristotle also reports that the Pythagoreans identified contraries or opposites and organized them in a table of 10 fundamental pairs: limited and unlimited, odd and even, one and plurality, right and left, male and female, resting and moving, straight and curved, light and darkness, good and bad, square and oblong. This table of opposites reflects the Pythagorean attempt to organize all of reality into a systematic structure based on mathematical principles. The first pair, limited and unlimited, corresponds roughly to form and matter, to definite structure and indefinite potentiality. The opposition of odd and even numbers served as a basic instance of this polarity. From these fundamental opposites, the Pythagoreans attempted to derive or explain other features of reality. This approach again anticipates later philosophical developments. Plato's theory of forms involves a similar contrast between determinate forms and the indeterminate receptacle in which they are instantiated. Aristotle's hylomorphism distinguishes form and matter as fundamental metaphysical principles. In both cases, we see the influence of Pythagorean thinking about limit, definition, and mathematical structure as principles of intelligibility. The conviction that reality exhibits systematic organization, that opposites form complementary pairs, that diverse phenomena can be understood through relatively few fundamental principles, all these ideas central to later Greek philosophy have Pythagorean roots. The question of how numbers relate to physical objects preoccupied ancient interpreters of Pythagoreanism. If things are numbers, are they identical with numbers in a strict sense? Are they constituted by numbers as by material components? Do they participate in numbers as Platonic objects participate in forms? Are they simply structured according to numerical relationships without literally being numbers? Different passages in Aristotle's account suggest different interpretations, and scholars continue to debate which best captures early Pythagorean doctrine. The interpretive difficulties reflect genuine philosophical problems about the relationship between abstract mathematical entities and concrete physical objects, problems that remain active in contemporary philosophy of mathematics. Some modern scholars argue that the Pythagoreans distinguished between mathematical numbers, the objects of arithmetic, and physical numbers, the units that compose material things. On this reading, when the Pythagoreans said things are numbers, they meant that physical objects consist of discrete units related in definite ways, not that objects are identical with the abstract numbers of mathematical theory. A physical object might be composed of, say, 12 units arranged in a rectangular array, but this is different from saying it is the number 12. This interpretation makes Pythagorean metaphysics more coherent by separating mathematical objects from their physical instantiations, but it may import later distinctions that the early Pythagoreans themselves did not clearly formulate. Other scholars emphasize the Pythagorean view that mathematical objects have a kind of reality intermediate between the purely abstract and the purely physical. Numbers and geometric forms exist eternally and independently of human thought, but they are manifested in or instantiated by physical objects. The circle exists as a mathematical form, but actual circular objects exhibit this form imperfectly. The ratio 2:1 exists as a mathematical relationship, but it is realized in musical octaves and in other physical proportions. On this view, Pythagorean ontology includes 3 levels: mathematical entities, physical instantiations of mathematical entities, and perhaps also ideas or forms transcending both. This reading brings Pythagoreanism closer to Platonism and may reflect later developments influenced by Plato rather than original Pythagorean doctrine. Whatever the precise metaphysical picture, the Pythagorean emphasis on number as the key to understanding reality expressed several philosophical commitments that would prove enormously influential. First, the conviction that reality is intelligible, that the human mind can grasp the principles underlying natural phenomena through reason and inquiry. Second, the recognition that mathematics provides powerful tools for understanding nature, that quantitative analysis reveals patterns and relationships invisible to ordinary observation. Third, the idea that beneath apparent diversity and change lie stable, eternal structures that explain and unify phenomena. Fourth, the notion that beauty, harmony, and order are objective features of reality, rooted in mathematical relationships, not merely subjective responses. These commitments shape the subsequent development of natural philosophy and science. The Pythagorean number philosophy also implied an epistemological stance. If reality is fundamentally mathematical, then knowledge of reality requires mathematical understanding. Sense perception alone cannot grasp the essential nature of things, for perception presents us only with changing appearances, particular instances, qualitative features. Mathematical knowledge, by contrast, concerns eternal truths, universal principles, quantitative relationships. To know reality in the deepest sense is to understand the mathematical structure that makes things what they are. This valorization of mathematical knowledge over sensory experience influenced Plato profoundly, and through him shaped the Western philosophical tradition's general tendency to privilege abstract reason over embodied perception. At the same time, the Pythagorean approach raised questions that subsequent philosophers would struggle to answer. If reality is mathematical, what about qualities like colour, warmth, pleasure, which do not seem reducible to number? Are these merely subjective appearances with no foundation in reality's mathematical structure? Or do they too have some numerical basis we have not yet discovered? If mathematical entities are real and eternal, where and how do they exist? Are they in some transcendent realm, as Plato would suggest? Are they abstractions from physical instantiations, as Aristotle would argue? Or is their mode of existence something entirely different? If mathematics describes reality so successfully, why? Is this because reality is inherently mathematical, or because mathematics is simply an extremely useful tool for organizing experience? These questions, first raised by Pythagorean philosophy, remain active in contemporary thought. Philosophers of mathematics debate whether mathematical entities exist independently of human minds, whether mathematical truths are discovered or invented, whether mathematics describes an objective reality or merely provides useful fictions. Philosophers of science debate whether the success of mathematical physics shows that reality is fundamentally mathematical or merely that mathematics is an effective descriptive tool. The Pythagorean claim that all is number initiated a conversation that continues across 2.5 millennia. The boldness of the Pythagorean thesis should not be underestimated. To propose that reality in its fundamental nature is mathematical, that number is not just a property of things, but their very essence, was to break radically with ordinary understanding. Common sense holds that objects are made of material stuff, that they have various qualities and properties, that numbers are at most one feature among many. The Pythagoreans inverted this picture, treating mathematical structure as primary and sensible qualities as secondary or derivative. This inversion required both remarkable mathematical insight and considerable philosophical audacity. It established a paradigm that would recur whenever thinkers emphasized formal, structural, or mathematical analysis over material, qualitative, or phenomenological description. Among the symbols and teachings of Pythagorean philosophy, none held greater significance than the Tetractys, the triangular arrangement of the first 4 integers that sum to 10. This simple geometric figure, composed of 10 points arranged in 4 rows with 1, 2, 3, and 4 points respectively, embodied fundamental cosmological principles and mathematical relationships. The Pythagoreans regarded the Tetractys with reverence, swearing oaths upon it and treating it as a key to understanding the structure of reality. To modern eyes, the intense philosophical and even religious significance attached to this pattern may seem excessive, but careful examination reveals that the Tetractys encapsulated sophisticated insights about number, geometry, harmony, and cosmic order. It served simultaneously as mathematical theorem, metaphysical principle, and meditation object, uniting diverse strands of Pythagorean thought in a single elegant symbol. The Tetractys takes its visual form from a triangular arrangement. At the apex sits a single point, representing the number 1 and the principle of unity. Below it, 2 points form a row, representing the number 2 and the principle of duality. The third row contains 3 points, representing 3 and the principle of completion or harmony. The fourth and final row contains 4 points, representing 4 and the principle of material extension. Together, these 4 rows of 1, 2, 3, and 4 points sum to 10, the decade, which the Pythagoreans considered the perfect number. This perfection derived not from arbitrary preference, but from the mathematical fact that 10 contains all the essential numbers and returns to unity, as the digits begin again with 11 as 1 plus 10, 12 as 2 plus 10, and so forth. The numerical significance of the Tetractys begins with the simple arithmetic equation 1 plus 2 plus 3 plus 4 equals 10. This sum represents the first triangular number greater than unity, the first instance of a pattern that continues with 6, 10, 15, 21, and so on. Triangular numbers, those that can be arranged in triangular patterns, were studied extensively by the Pythagoreans, who investigated their properties and relationships. The Tetractys, as the triangular arrangement of 10 points, instantiates both the concept of triangular number and the specific perfection of the decade. It demonstrates visually the relationship between the generating numbers 1 through 4 and their sum 10, making abstract arithmetic relationship concrete and perceivable. But the mathematical significance of the Tetractys extends far beyond this basic sum. The four numbers of the Tetractys, 1, 2, 3, and 4, generate through their ratios the fundamental musical consonances. The ratio 2:1 produces the octave, the most basic harmonic interval. The ratio 3:2 produces the perfect fifth, the next most consonant interval. The ratio 4:3 produces the perfect fourth, completing the principal consonances of Greek music theory. Thus, the Tetractys contains within itself the mathematical basis of musical harmony. It shows that the entire system of harmonious relationships emerges from the first four numbers, that cosmic harmony is founded on the simplest numerical principles. These musical ratios also embed within them mathematical relationships among the numbers themselves. Notice that the ratio 3:2 times the ratio 4:3 equals 2:1, since 3/2 times 4/3 equals 12/6 equals 2 ones. This means that the perfect fifth combined with the perfect fourth produces an octave, a relationship basic to Greek musical theory and practice. The Tetractys thus encodes not only the fundamental intervals, but also their mathematical relationships and combinations. It reveals harmony as a system of proportions derivable from first principles, as a structure graspable by reason and expressible in exact numerical terms. The geometric significance of the Tetractys lies in its representation of dimension. The top point corresponding to 1 represents the geometric point, that which has position but no extension. 2 points determine a line, the first dimension of extension. 3 points, not in a straight line, determine a plane, the second dimension. 4 points, not in a plane, determine a solid, the third dimension. Thus, the Tetractys contains the progression from zero-dimensional point to one-dimensional line, to two-dimensional plane, to three-dimensional solid, the complete hierarchy of geometric possibilities. The Pythagoreans saw in this progression a cosmic principle, the generation of the spatial world from simple principles through successive stages of increasing complexity. This geometric interpretation of the Tetractys connected directly to the metaphysical doctrine of how plurality emerges from unity. The number 1 represents undifferentiated unity, the absolute principle before any distinction. 2 represents the first division, the emergence of duality, the principle of otherness that makes multiplicity possible. 3 represents the first return to unity, the harmonious resolution of opposition, the triad that the Pythagoreans associated with beginning, middle, and end. 4 represents completion, the realization of structure in material extension, the solid body existing in three-dimensional space. The sequence 1, 2, 3, 4 thus describes a metaphysical cosmogony, the process by which the material world emerges from original unity through successive stages of differentiation and determination. The Pythagoreans further elaborated the significance of each number within the Tetractys. 1, the monad, is both number and not number, the source from which other numbers arise, but not itself a plurality. It represents unity, identity, the principle of being. The Pythagoreans associated it with reason and with the divine. 2, the dyad, represents division, difference, and multiplicity. It is the principle of otherness, of opposition, of the unlimited. The Pythagoreans associated it with opinion rather than knowledge, with appearance rather than reality. 3, the triad represents harmony, the reconciliation of unity and division. It is the first proper number, the first to have beginning, middle, and end. 4, the tetrad represents completion, stability, and manifestation. It is associated with justice, with the solid, with the material world. Beyond these individual meanings, the relationships among the numbers of the Tetractys carried philosophical significance. The sum of 1 and 2 equals 3, suggesting that harmony emerges from unity and division. The sum of 1, 2, and 3 equals 6, another perfect number in Pythagorean terms, one whose factors sum to itself. The sum of all four numbers equals 10, which itself can be represented as 1 followed by 0, a return to unity at a higher level. These numerical relationships were not mere arithmetic curiosities, but were understood as revelations of cosmic order, as patterns reflecting the fundamental structure of reality. The perfect decade, 10, held special importance in Pythagorean cosmology beyond its role as the sum of the Tetractys. 10 is the first number to require double-digit notation, the first to explicitly manifest the principle of place value. It serves as the base of the most natural counting system, likely because human beings have 10 fingers. The Pythagoreans noted that 10 comprehends all numbers, in the sense that all integers can be represented through combinations of 10 with the digits 0 through 9. They regarded 10 as complete and self-sufficient, a number containing all numerical possibilities. The cosmological applications of the Tetractys extended to astronomy. Some Pythagorean thinkers, notably Philolaus, developed a cosmological model featuring 10 bodies orbiting a central fire. This model, which preceded the heliocentric hypothesis by nearly 2 millennia, placed at the center of the cosmos not the Earth, but an invisible fire called the hearth of the universe. Around this central fire orbited 10 bodies, the sphere of fixed stars, the 5 planets known to antiquity, the Sun, the Moon, the Earth, and a counter-Earth. This counter-Earth was postulated to exist on the opposite side of the central fire, forever hidden from terrestrial observation. While modern readers might dismiss the counter-Earth as ad hoc invention designed to reach the sacred number 10, we should recognize that ancient astronomy involved both observational data and theoretical principles, and that the Pythagoreans were attempting to construct a mathematically elegant and philosophically coherent account of celestial phenomena. The geometric properties of the Tetractys invited contemplation and meditation. The triangular form itself embodies stability, with a broad base supporting the apex. The internal structure reveals multiple smaller triangles, 4 triangles of size 1, 3 of size 2, 2 of size 3, and 1 of size 4. These nested triangles demonstrate how complex structures emerge from simple elements, how the whole contains and organizes its parts. The symmetry and balance of the figure reflect aesthetic principles that the Pythagoreans associated with goodness and beauty. To meditate on the Tetractys was to contemplate the fundamental principles of order, proportion, and harmony that structure reality. The Pythagoreans also found in the Tetractys relationships among different types of means or averages. The arithmetic mean of 2 numbers is their sum divided by 2. The geometric mean is the square root of their product. The harmonic mean is defined so that it stands in the same relationship to the 2 original numbers as their difference stands to each other. These 3 types of means, central to later Greek mathematical theory, can all be illustrated using the numbers of the Tetractys. The relationships among these means connected to both musical theory and the Pythagorean understanding of proportion and just relationships. The sacred status of the Tetractys within the Pythagorean community expressed itself in ritual and oath. The traditional Pythagorean oath invoked the Tetractys as witness and guarantee of truthfulness. To swear by the Tetractys was to swear by the most sacred principle, the foundation of cosmic order itself. This practice reflects the integration of mathematical insight with religious devotion, characteristic of Pythagoreanism. The Tetractys was not merely an interesting mathematical pattern, but a sacred symbol, a manifestation of divine wisdom, a key to understanding the deepest mysteries of existence. That an abstract geometric figure could carry such freight of meaning indicates how thoroughly the Pythagoreans had integrated their mathematical discoveries into a comprehensive philosophical and spiritual worldview. Critics of Pythagoreanism, ancient and modern, have sometimes dismissed the Tetractys and its associated teachings as numerological mysticism disconnected from serious mathematical or philosophical thought. Aristotle, while respecting Pythagorean mathematical achievements, expressed skepticism about claims that cosmic principles could be read off from such simple numerical patterns. Modern philosophers often regard the reverence for the Tetractys as an example of how mathematical insight can be distorted by symbolic thinking and speculative extrapolation. Yet these criticisms may underestimate the sophistication of Pythagorean thought. The Tetractys encoded genuine mathematical relationships, the generation of triangular numbers, the ratios underlying musical harmony, the dimensional structure of geometric space. That the Pythagoreans elaborated these insights into a comprehensive cosmology and treated the symbol with religious reverence does not invalidate the mathematical core. The influence of the Tetractys extended beyond the immediate Pythagorean school. Plato's Timaeus, the dialogue presenting his most detailed cosmology, shows clear Pythagorean influence in its emphasis on mathematical structure, harmonic relationships, and geometric forms as principles of cosmic order. The Neoplatonists of late antiquity revived interest in Pythagorean number symbolism and incorporated the Tetractys into their metaphysical systems. Medieval Christian philosophers, encountering Pythagorean ideas through Boethius and other transmitters of ancient wisdom, found in the Tetractys an image of divine creation and providential order. Renaissance humanists, recovering ancient texts and seeking universal wisdom, studied Pythagorean number philosophy and geometric symbolism. The Tetractys remained a living symbol across these transformations, continually reinterpreted, but retaining its core associations with harmony, order, and mathematical elegance. In understanding the Tetractys, we confront a central feature of Pythagorean philosophy: the interweaving of mathematics, metaphysics, aesthetics, and spiritual practice into a unified vision. The Tetractys functioned simultaneously at multiple levels. As mathematics, it demonstrated genuine theorems about triangular numbers, musical ratios, and geometric dimension. As metaphysics, it provided a model for understanding how multiplicity emerges from unity and how the cosmos exhibits intelligible structure. As aesthetics, it embodied principles of symmetry, proportion, and harmony that the Pythagoreans regarded as constitutive of beauty. As spiritual symbol, it focused meditation and expressed reverence for the rational order of reality. This multivalent functionality reflects a way of thinking about mathematics and philosophy that modern disciplinary specialization has largely obscured. The Tetractys reminds us that for the Pythagoreans, mathematics was never merely technical calculation or formal manipulation of symbols. It was an investigation into the fundamental nature of reality, a spiritual discipline, and a path to wisdom. The patterns discovered in number and geometry were not arbitrary human constructions, but objective features of the cosmos, revelations of its rational structure. To study these patterns, to contemplate their relationships, to recognize their manifestations in music, astronomy, and nature, was to align one's mind with cosmic order and to participate in the divine intelligence that structures all things. Whether we find this view of mathematics compelling or not, engaging with it enriches our understanding of how philosophy and science have been conceived, of the range of meanings mathematical practice can bear, and of the perennial human aspiration to find unity and intelligibility in the apparent chaos of experience. The Pythagorean school made fundamental contributions to mathematics that transformed it from a collection of practical techniques into a systematic theoretical discipline. These contributions included specific theorems and problem solutions, but more importantly, they established new standards of rigor, introduced the concept of mathematical proof, and demonstrated that mathematical truths hold with necessity and universality. The most famous result attributed to the school, the Pythagorean theorem relating the sides of right triangles, represents just one achievement among many. The Pythagoreans investigated properties of numbers, developed geometric methods, explored mathematical relationships, and began the project of organizing mathematical knowledge into logical structures. Their work laid foundations for the systematic mathematics of Euclid and for the entire subsequent tradition of deductive mathematical reasoning. Yet their mathematical investigations also precipitated a crisis when they discovered that not all geometric magnitudes correspond to rational numbers, a discovery that challenged fundamental assumptions and required substantial conceptual innovation to address. The theorem that bears Pythagoras' name states that in any right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. If we denote the sides as A and B and the hypotenuse as C, the relationship is C squared equals a squared plus B squared. This theorem was known in Babylon and probably in Egypt before the time of Pythagoras, used in practical surveying and construction. What the Pythagorean school added was mathematical proof, a demonstration showing that the theorem holds not just in measured cases, but necessarily and universally for all right triangles whatsoever. This shift from empirical observation to deductive proof marks a crucial development in human thought, the recognition that certain truths can be established with absolute certainty through logical reasoning from clearly stated principles. Several different proofs of the Pythagorean theorem were known in antiquity, and we cannot determine with certainty which, if any, was due to Pythagoras himself. One elegant proof uses a diagram showing how squares constructed on the sides of a right triangle can be dissected and rearranged to demonstrate the equality. Another proof employs the properties of similar triangles and proportions. Still another uses algebraic manipulation of areas. What matters historically is not which specific proof was first, but that the Pythagorean school established proof as the standard of mathematical knowledge. A mathematical claim is not known to be true merely because it seems obvious or because measurement confirms it in particular cases. It is known to be true when it has been derived through valid reasoning from accepted principles. This emphasis on proof required the development of clear definitions, explicit axioms, and rules of inference. The Pythagoreans began to organize mathematical knowledge systematically, identifying basic concepts that required definition, fundamental principles that could be taken as starting points, and methods of reasoning that preserve truth. This organizational project reached its culmination in Euclid's Elements, written more than 2 centuries after Pythagoras, but the basic approach originates with the Pythagorean school. The Elements begin with definitions of point, line, surface, and other basic concepts, proceed to postulates and common notions taken as self-evident truths, and then derive hundreds of theorems through rigorous logical deduction. This axiomatic deductive structure, paradigmatic of mathematical reasoning ever since, has Pythagorean origins. The Pythagoreans studied extensively the properties of different classes of numbers. They distinguished odd from even numbers and investigated their behaviors under arithmetic operations. They recognized prime numbers, those divisible only by themselves and 1, and composite numbers, those with other factors. They studied perfect numbers, those equal to the sum of their proper divisors, with 6 as the first example, since 1 plus 2 plus 3 equals 6. They investigated figurate numbers, triangular numbers like 3, 6, and 10, which can be arranged in triangular patterns, square numbers like 4, 9, and 16, which form square arrays, and higher dimensional analogues. They discovered relationships among these classes. For example, that the sum of 2 consecutive triangular numbers is always a square number. Number theory in the Pythagorean tradition was not merely abstract pattern finding, but was understood as investigation into the fundamental structure of reality. Each class of numbers was thought to have particular properties and significance. Even numbers were associated with the female principle, divisibility, and the unlimited. Odd numbers were associated with the male principle, indivisibility, and the limited. Prime numbers, which resist division into equal parts, possessed special status. Perfect numbers, with their internal balance and completeness, were regarded as particularly beautiful and significant. This blending of mathematical investigation with philosophical and even mystical interpretation characterized Pythagorean number theory and gave it a richness that purely technical mathematics might lack. Geometric investigation in the Pythagorean school began with study of the basic figures: triangles, squares, pentagons, and other polygons. The Pythagoreans proved various theorems about these figures, including results about the angles of triangles, the properties of regular polygons, and relationships among different geometric shapes. They investigated the 5 regular solids, the 3-dimensional figures whose faces are all identical regular polygons, the tetrahedron with 4 triangular faces, the cube with 6 square faces, the octahedron with 8 triangular faces, the dodecahedron with 12 pentagonal faces, and the icosahedron with 20 triangular faces. The proof that exactly 5 such regular solids exist represents a significant mathematical achievement, requiring systematic analysis of the possibilities and demonstration that no others are possible. The Pythagorean interest in regular solids connected to their cosmological speculations. Some later Pythagoreans and Plato in the Timaeus associated the regular solids with the elements, the tetrahedron with fire, the cube with earth, the octahedron with air, and the icosahedron with water. The dodecahedron was associated with the cosmos as a whole, or with a 5th element. While modern readers may regard these associations as fanciful, they reflect a serious attempt to connect mathematical structure with physical reality, to find geometric forms that underlie material phenomena. The question of why nature exhibits particular geometric forms, why certain structures recur in different contexts, remains scientifically significant, even if the specific Pythagorean answers have been superseded. The most dramatic mathematical discovery of the Pythagorean school was the existence of incommensurable magnitudes, geometric quantities that cannot be expressed as ratios of whole numbers. This discovery is traditionally associated with Hippasus of Metapontum, though the legend surrounding it may be later invention. The simplest case involves the diagonal of a square. Consider a square with side length 1. By the Pythagorean theorem, the square of the diagonal equals 1 squared plus 1 squared equals 2. Therefore, the diagonal has length equal to the square root of 2, but it can be proven that the square root of 2 cannot be expressed as the ratio of 2 integers. This proof, likely discovered by the Pythagoreans, proceeds by reductio ad absurdum, showing that the assumption that root 2 equals some ratio of integers leads to contradiction. The existence of irrational numbers, as we now call them, posed a fundamental challenge to Pythagorean philosophy. If all is number, and a number was understood as whole numbers and their ratios, what are we to make of geometric magnitudes that escape this framework? The diagonal of a square clearly exists as a geometric object. We can draw it, measure it, use it in constructions. Yet it cannot be expressed using the numbers the Pythagoreans recognized. This discovery threatened the foundations of Pythagorean mathematics and metaphysics. It showed that geometric reality is richer than arithmetic, that continuous magnitudes cannot be reduced to discrete units, that the mathematical structure of reality is more complex than the simple doctrine that all is number seemed to imply. The Pythagorean response to this crisis involved several developments. One was increased emphasis on geometric methods over purely arithmetic ones. If not all magnitudes are expressible numerically, then geometry must be developed on its own terms, with methods appropriate to continuous quantities rather than discrete numbers. This approach culminated in the geometric algebra of Euclid's Elements, which handles relationships among magnitudes geometrically rather than numerically. A second response was the development of a theory of proportion applicable to both commensurable and incommensurable magnitudes. This theory, perfected by Eudoxus and presented in Book 5 of Euclid's Elements, provides rigorous definitions of ratio and proportion that work for any magnitudes, not just those expressible as whole numbers. A third response was philosophical reinterpretation of the doctrine that all is number. Rather than claiming that everything literally is or can be expressed as whole numbers and their ratios, later, Pythagorean thought emphasized that everything exhibits mathematical structure and relationships, even if some of these relationships involve magnitudes beyond simple numerical ratios. The fundamental insight that reality is mathematically ordered, that it exhibits proportion and harmony, that it is intelligible through mathematical reasoning, all this could be preserved even while acknowledging that the specific claim about whole numbers required refinement. The discovery of irrationals illustrates how mathematical investigation can challenge and refine philosophical doctrines. The Pythagoreans began with a bold metaphysical thesis: reality is fundamentally numerical. Mathematical research, pursued rigorously, revealed complexities that the original formulation could not accommodate. Rather than abandoning either the mathematics or the philosophy, the tradition adapted, developing more sophisticated mathematical techniques and more nuanced philosophical positions. This dialectic between theory and discovery, between metaphysical commitment and mathematical result, characterizes much of the subsequent history of mathematics and philosophy of mathematics. The Pythagorean school's contributions to proof and rigor transformed mathematics into a deductive science. Before the Pythagoreans, mathematical knowledge consisted largely of rules and procedures, recipes for computing areas, methods for solving particular problems, techniques passed down and refined through practice. The Pythagoreans transformed mathematics into a systematic body of knowledge organized by logical principles. They asked not just how to solve problems, but why solutions work, what makes them necessarily correct. They sought to understand the structure of mathematical domains, the relationships among concepts, the foundations on which specific results rest. This transformation was philosophical as much as mathematical, reflecting questions about the nature of knowledge, the standards of certainty, and the relationship between particular facts and general principles. The pedagogical methods of the Pythagorean school reinforce this emphasis on understanding over mere technique. Students were not simply taught procedures, but were led to discover relationships themselves, to formulate proofs, to question assumptions. The tradition of posing problems for investigation, of collective mathematical work, of dialectical examination of proposed solutions, all these practices fostered mathematical creativity and rigor. Mathematics became not a static body of techniques, but an active inquiry, a living tradition of problem posing and problem solving, of conjecture and proof, of discovery and systematization. The mathematical work of the Pythagorean school extended beyond geometry and number theory to other areas as well. They investigated numerical aspects of music theory, as we have noted, deriving the scale from arithmetic ratios. They made astronomical observations and attempted to account for celestial phenomena through mathematical models. They studied ratios and proportions in art and architecture, developing principles of aesthetic design. They explored mathematical puzzles and recreational problems. This breadth of application demonstrated the scope of mathematical reasoning, its relevance to diverse domains, its power to illuminate apparently unrelated phenomena by revealing underlying structural relationships. The Pythagorean emphasis on mathematical proof established standards that continue to govern mathematics. A mathematical claim today is accepted as theorem only when it has been proven, when a rigorous argument has been given showing that it follows from accepted axioms by valid logical steps. Merely probable arguments, empirical evidence, appeals to intuition, or arguments from authority do not suffice. This insistence on proof as the criterion of mathematical knowledge originates with the Pythagorean school and represents one of their most important intellectual contributions. It gave mathematics a unique epistemological status as a domain where certain knowledge is possible, where truths can be established beyond any reasonable doubt, where human reason can attain its fullest rigor and clarity. Yet the Pythagorean conception of proof differed in important ways from modern standards. Ancient proofs often relied on diagrams and geometric intuition in ways that later mathematicians would regard as insufficiently rigorous. The line between axioms and theorems, between what is assumed and what requires proof, was not always clearly drawn. The role of definitions and the criteria for acceptable definitions were matters of ongoing debate. The discovery of irrationals revealed that mathematical concepts themselves required careful analysis and could not be taken as intuitively given. All these issues would be addressed and refined over centuries of mathematical development, but the basic project of organizing mathematics as a deductive system grounded in proofs has remained constant since the Pythagorean innovation. The traditional account attributes the discovery of musical ratios to Pythagoras himself through observation of a blacksmith's workshop. According to this legend, Pythagoras noticed that hammers of different weights striking anvils produced tones of different pitches, and that certain combinations of tones sounded harmonious while others sounded discordant. Investigating systematically, he determined that harmonious intervals corresponded to simple numerical ratios. Weights in the ratio 2:1 produced an octave, 3:2 produced a perfect fifth, 4:3 produced a perfect fourth. This story, while almost certainly apocryphal, captures the essential insight that musical consonance is not arbitrary or conventional, but depends on precise mathematical relationships. The actual Pythagorean experiments likely involved not hammers and anvils, but vibrating strings. When a string is plucked or struck, it vibrates at a frequency determined by its length, tension, and mass. For strings of the same material under the same tension, frequency is inversely proportional to length. A string half as long vibrates twice as fast and sounds a tone 1 octave higher. A string 2/3 as long vibrates 1.5 times as fast and sounds a perfect fifth higher. A string 3/4 as long vibrates 1.3 times as fast and sounds a perfect fourth higher. These simple length ratios, 2:1, 3:2, and 4:3, correspond exactly to the frequency ratios that produce the fundamental consonances. The Pythagoreans verified these relationships experimentally. They constructed a device called a monochord, a single string stretched over a resonating chamber with a movable bridge that could divide the string at different points. By moving the bridge to create different length ratios and listening to the resulting intervals, they confirmed that simple whole number ratios produced harmonious sounds while more complex ratios produced dissonance. They systematized these observations into a theory of musical intervals based on mathematical proportion. They recognized that the same ratios appeared whether one considered string lengths or the frequencies of vibration, establishing that these mathematical relationships were fundamental to the phenomenon of musical harmony. This discovery had several profound implications. First, it showed that mathematics applies not just to geometrical shapes and numbers in the abstract, but to physical phenomena and sensory experience. The beauty of musical harmony which seems quintessentially qualitative and subjective, actually depends on objective mathematical relationships. This suggested that other aspects of experience might similarly rest on mathematical foundations, that quantity underlies quality, that the rational structure of reality manifests even in domains we might regard as purely aesthetic or subjective. Second, the discovery provided concrete evidence for the Pythagorean doctrine that number is the principle of all things. Here was a clear case where numerical ratios literally constituted a phenomenon, where the what it is of musical harmony consisted in mathematical relationships. The octave simply is the 2-to-1 ratio. The perfect fifth is the 3-to-2 ratio. These are not descriptions of pre-existing musical relationships, but definitions of what these intervals are. The mathematics is not added to the music, but constitutes it. Third, the discovery revealed a deep connection between mathematics and aesthetic value. Beautiful sounds correspond to simple mathematical ratios. This suggested a general principle, that beauty consists in mathematical order, proportion, and harmony. The Pythagoreans extended this principle beyond music to architecture, sculpture, painting, and poetry. They sought mathematical proportions in well-designed buildings, harmonic relationships in pleasing visual compositions, numerical patterns in excellent poetry. This mathematical aesthetics profoundly influenced Greek art and thought, and has recurred in various forms throughout Western culture. The mathematical theory of musical harmony rested on analysis of ratios and proportions. A ratio is a relationship between two quantities. The ratio of 4-to-3 compares these two numbers. A proportion is an equality of ratios. The statement that 4:3 as 8:6 expresses that these two ratios are equivalent. The Pythagoreans developed an elaborate theory of proportions, distinguishing different types of means or averages, investigating properties of proportional sequences, and applying proportional reasoning to diverse problems. This mathematical framework proved applicable far beyond music, providing tools for astronomy, architecture, mechanics, and other domains. The fundamental musical ratios generated by the Tetractys, the numbers 1 through 4, produced the consonant intervals recognized by Greek music theory. The octave, with ratio 2-to-1, divides the musical scale into 8 steps and returns to the same note at a higher pitch. The perfect fifth, with ratio 3-to-2, and the perfect fourth, with ratio 4-to-3, are the next most consonant intervals. Combining these intervals generates the complete Greek musical system. 2/4 make a seventh, a fourth and a fifth make an octave, 2/5 make a ninth, and so on. The entire structure of Greek music derives from these simple ratios rooted in the Tetractys. Why do these simple ratios sound consonant while more complex ratios sound dissonant? The Pythagoreans offered several explanations. One emphasized that simple ratios reflect unity and order, while complex ratios reflect multiplicity and disorder. When two tones stand in a simple ratio, they blend harmoniously because their relationship is ordered and intelligible. When two tones stand in a complex ratio, they clash because their relationship lacks this clear order. Another explanation invoked the physical vibrations of strings. Simple ratios mean that the vibration patterns of the two strings align regularly, reinforcing each other, while complex ratios mean the patterns interfere irregularly, creating beats and roughness. Modern acoustical theory explains consonance and dissonance in terms of frequency ratios and the harmonic overtone series. When a string vibrates, it produces not just a single frequency, but a spectrum of frequencies, the fundamental and its overtones at integer multiples of the fundamental frequency. When two notes are played together, consonance occurs when the overtone spectra align well, sharing many common frequencies, while dissonance occurs when the spectra interfere. Simple frequency ratios correspond to good alignment of overtone spectra. The mathematical relationships the Pythagoreans discovered thus reflect deep facts about the physics of vibration, even though the Pythagoreans themselves lacked this theoretical understanding. The Pythagorean musical system, based on ratios involving the numbers 1 through 4, could not generate all the intervals required for a complete musical scale. Attempting to construct a scale using only perfect fifths and fourths leads to mathematical inconsistencies. The ratios do not close properly, and small discrepancies accumulate. This problem, known as the Pythagorean comma, troubled ancient music theorists and led to various proposed solutions. Some accepted slight imperfections in tuning. Others developed alternative tuning systems with different mathematical bases. Others divided intervals in ways that compromised pure ratios in favor of practical playability. These technical issues in music theory drove mathematical research into ratios, proportions, and number theory. The Pythagorean understanding of musical harmony influenced theories of the human soul and its proper ordering. Just as musical harmony results from correct proportions among tones, so psychological harmony results from correct proportions among the parts of the soul. Plato's Republic presents a tripartite soul with reason, spirit, and appetite, and defines justice as a harmony among these parts, analogous to musical harmony. Each part must perform its proper function and stand in right relationship to the others. Excess or deficiency in any part destroys this harmony, just as wrong proportions destroy musical consonance. The ethical life aims at achieving and maintaining psychological harmony, at tuning the soul properly. This musical psychological analogy extended to medicine and health. The Pythagoreans and later Greek physicians regarded health as a balance or harmony of bodily elements and qualities. Disease resulted from imbalance, from excess or deficiency, disturbing proper proportions. Treatment aimed at restoring balance through diet, exercise, and other interventions. Music itself could serve as medicine, as therapeutic use of harmony to restore psychological or even physical health. The physician Hippocrates and the medical writers influenced by Pythagoreanism applied concepts of proportion, balance, and harmony to their theories of health and disease. The Pythagoreans practiced music as spiritual discipline and philosophical training. They believed that listening to properly harmonious music could order the soul, calm the passions, and prepare the mind for philosophical contemplation. Different musical modes had different effects. Some modes energized and excited, others calmed and soothed. By choosing appropriate music, one could influence psychological states and cultivate virtues. This therapeutic and educational use of music remained important throughout ancient philosophy. Plato discusses at length which musical modes are appropriate for the education of guardians in the ideal city, rejecting certain modes as promoting weakness or licentiousness, and embracing others as fostering courage and temperance. The Pythagorean discovery of musical ratios established mathematics as an essential tool for understanding natural phenomena. It showed that what appears in experience as qualitative difference, as the pure quality of sound, actually reflects quantitative relationships. It demonstrated that measurement and calculation can reveal truths about reality that remain hidden to unaided perception. It suggested that the cosmos operates according to mathematical laws, that nature exhibits mathematical structure, and that human reason, through mathematics, can grasp this structure. These insights laid conceptual foundations for natural science, for the project of explaining natural phenomena through mathematical models and quantitative laws. The extension of harmonic theory from music to cosmology and natural philosophy will be considered in the next chapter, but we should note here that the musical discoveries themselves made this extension plausible. If the beauty and order of music rest on mathematical foundations, why should not the beauty and order of the cosmos rest on similar foundations? If audible harmony results from simple numerical ratios, might not the visible harmony of celestial motions result from analogous mathematical relationships? The Pythagorean doctrine of the music of the spheres applied principles discovered in acoustics to astronomy, seeking cosmic harmony on the grandest scale. Whether or not this extension was scientifically fruitful, it reflected a methodological principle that successful mathematical explanation in one domain suggests attempting mathematical explanation in others, that unified understanding of diverse phenomena may come through recognizing common mathematical structures. The Pythagorean mathematical aesthetics influenced architecture and visual art. Architects sought to incorporate harmonic proportions in building design, using ratios related to those found in music. The golden ratio, though not explicitly articulated by early Pythagoreans, became associated with Pythagorean aesthetics in later tradition and was thought to embody perfect proportion. Sculptors and painters sought balanced compositions based on mathematical relationships. While the extent to which practicing artists consciously applied mathematical principles is debated, the aesthetic ideal of proportionate design grounded in mathematical harmony definitely shaped Greek and later Western art. The integration of mathematics, music, and philosophy in Pythagorean thought established a model of comprehensive education. To be educated meant mastering the mathematical sciences, not just as technical skills, but as windows into reality's structure. Music was included among these sciences because of its mathematical basis. Astronomy, as we shall see, was studied for similar reasons. Geometry and arithmetic formed the foundation. These four mathematical disciplines, later systematized as the quadrivium in medieval education, constituted the core of liberal education for over 1,000 years. This educational tradition has Pythagorean origins, reflecting the Pythagorean conviction that mathematical understanding is essential to wisdom and that the various mathematical sciences illuminate different aspects of cosmic order. The Pythagorean doctrine of the music of the spheres extended their discovery of mathematical harmony in audible music to the cosmos itself, proposing that celestial bodies in their motions produce harmonious tones according to the same mathematical ratios that govern terrestrial music. This cosmic music, though inaudible to human ears habituated to its constant presence, structures the entire universe as a grand harmonic system. The doctrine represents both a remarkable speculative extension of scientific insight and a profound philosophical vision of cosmic unity, order, and beauty. It influenced ancient astronomy, shaped medieval cosmology, inspired Renaissance natural philosophy, and continues to serve as a powerful metaphor for cosmic order even in contemporary thought. To understand the music of the spheres is to grasp how the Pythagoreans moved from mathematical discoveries to comprehensive cosmological theory, how they unified physics and metaphysics, and how they conceived the relationship between human knowledge and cosmic structure. The basic idea underlying the music of the spheres is that motion produces sound, that celestial bodies moving through space must generate tones, and that the mathematical relationships governing celestial motions should mirror those governing musical harmony. Earthly objects in motion produce audible sounds. A thrown stone whistles through the air. A plucked string vibrates and resonates. Why should not the planets, the sun, the moon, the stars, in their vast motions also produce sounds? If the cosmos is as orderly and harmonious as the Pythagoreans believed, these celestial sounds should form consonant intervals, should exhibit the same mathematical ratios that make music beautiful, should constitute a cosmic symphony of perfect proportions. The reason we do not hear this celestial music, according to Pythagorean teaching, is not that it does not exist, but that we have heard it constantly from birth. Just as a blacksmith in his shop becomes habituated to the clanging of hammers and ceases to consciously hear it, so human beings are born into the sound of celestial harmony and take it as the background silence against which other sounds are measured. We are like fish in the ocean who, never having experienced anything but water, cannot perceive the water itself. The music of the spheres is so constant and all-encompassing that it escapes our notice, yet it structures the acoustic environment in which all earthly sounds occur. An alternative explanation for the inaudibility of cosmic music emphasized the human soul's fallen or embodied condition. Before birth, according to Pythagorean doctrines of metempsychosis, the soul existed in a purer state, either dwelling among the celestial spheres, or at least not imprisoned in material body. In that prior state, the soul could hear the celestial music directly. But entry into earthly embodiment dulls the soul's perceptive capacities, binding it to sensory perception and blocking access to higher realities. Through philosophical purification and contemplative practice, the soul might regain this lost capacity and become again aware of cosmic harmony. This explanation connected astronomical theory with spiritual doctrine, making celestial physics relevant to personal salvation. The astronomical models developed by Pythagorean thinkers attempted to describe celestial phenomena in mathematical terms consistent with the doctrine of cosmic harmony. The most innovative of these models was proposed by Philolaus of Croton, an important Pythagorean of the 5th century BCE. Philolaus rejected the traditional geocentric view that placed Earth at the centre of the cosmos, and instead posited a central fire called the hearth of the universe, around which all celestial bodies revolved. This central fire was not the sun, but a distinct cosmic entity, perhaps identified with divine reason or the principle of unity. 10 bodies orbited this central fire, the sphere of fixed stars, the 5 planets known to antiquity: Mercury, Venus, Mars, Jupiter, Saturn, the Sun, the Moon, Earth, and a counter-Earth. The counter-Earth, Antishthon in Greek, was positioned directly opposite Earth on the other side of the central fire, invisible to human observers because we always face away from it. The postulation of this counter-Earth has struck many later commentators as arbitrary, an ad hoc device to bring the total number of celestial bodies to the perfect decade. Yet it may have served genuine theoretical purposes. It could explain why lunar eclipses occurred more frequently than solar eclipses. The counter-Earth could block sunlight reaching the moon just as Earth could. It provided a way to account for observed irregularities in celestial motions, and it reflected the methodological principle that mathematical elegance and systematic completeness are guides to truth, that nature conforms to beautiful mathematical patterns. Philolaus's model was not heliocentric in the modern sense, since the Sun was not at the centre, but orbited the central fire along with other bodies. Yet it did remove Earth from the centre of the cosmos and treat it as one celestial body among others. This demotion of Earth was philosophically radical, challenging the natural human sense that Earth is the stable foundation and all else moves around it. It suggested that celestial and terrestrial phenomena might be subject to the same laws, that Earth participates in celestial motion rather than standing apart from it. These ideas would be developed by later Pythagorean astronomers and would influence Copernicus nearly 2,000 years later. The velocities and distances of celestial bodies in Philolaus's system were related by mathematical proportions. Faster-moving bodies or those at greater distances produced higher tones, while slower-moving or nearer bodies produced lower tones. The precise assignments of tones to bodies varied in different versions of the doctrine. Some accounts associated celestial bodies with the notes of a musical scale. Others related them to the fundamental consonances of octave, fifth, and fourth. Still others developed more complex harmonic relationships involving multiple ratios. The details are often unclear in surviving fragments, but the basic principle remained constant. Celestial motions exhibit the same mathematical ratios that govern musical harmony. Plato's Timaeus, while not explicitly Pythagorean, shows profound Pythagorean influence in its cosmology. The Timaeus describes the creation of the cosmos by a divine craftsman, the demiurge, who shapes reality according to eternal mathematical patterns. The world soul, which animates the cosmos and produces celestial motions, is constructed according to mathematical ratios related to musical intervals. Plato describes how the demiurge divides the world soul substance in ratios of 2:1, 3:2, and 4:3, the same ratios that produce the musical consonances. The resulting structure generates the motions of celestial bodies in harmonious relationships. Plato's cosmology thus incorporates the Pythagorean vision of a mathematically ordered, harmoniously moving cosmos. Aristotle, more skeptical of Pythagorean cosmology, addresses the doctrine of celestial harmony in his On the Heavens. He objects that if moving bodies produce sound proportionate to their size and velocity, the celestial spheres with their enormous size and tremendous speed should produce sounds of incredible intensity, enough to destroy everything on Earth. Since we observe no such effects, the theory must be false. The Pythagorean response that we do not hear the sound because we have always been accustomed to it seemed to Aristotle inadequate. He also questioned whether celestial bodies actually move through a medium that could transmit sound, noting that the heavens might be filled with ether, which does not propagate sound as air does. Despite Aristotle's criticisms, the doctrine of celestial harmony remained influential throughout antiquity and the Middle Ages. It appealed to the deep human intuition that the cosmos is ordered, beautiful, and meaningful. It provided a framework for integrating astronomy with music theory, both of which involved mathematics. It connected the systematic study of the heavens with aesthetic experience and spiritual aspiration. The idea that the universe is fundamentally harmonious, that its structure exhibits beauty and proportion, that understanding this harmony requires mathematical knowledge, all these aspects of the doctrine resonated with philosophers, astronomers, and theologians across centuries. Medieval Christian cosmology adapted the Pythagorean doctrine within a theological framework. God was understood as the cosmic musician who created the universe according to numerical proportions, who established celestial harmony at creation, and who maintains cosmic order through providential governance. The music of the spheres became an image of divine wisdom, a manifestation of the mathematical ideas in the divine mind according to which God fashioned the world. This Christianized Pythagoreanism appeared in thinkers like Boethius, whose De Institutione Musica transmitted ancient musical theory to the Middle Ages, and in the cosmological visions of Dante and other medieval poets. The Renaissance revival of interest in ancient philosophy brought renewed attention to Pythagorean ideas about cosmic harmony. Marsilio Ficino translated Plato's Timaeus and Iamblichus' Life of Pythagoras, making these texts widely available to Renaissance readers. Humanist scholars sought ancient wisdom in Pythagorean number mysticism. Natural philosophers attempted to discover harmonic relationships in nature. The vision of the cosmos as a grand musical instrument tuned by divine wisdom or mathematical necessity attracted those seeking to reconcile ancient philosophy with Christian theology and emerging natural science. Johannes Kepler, the great astronomer of the early 17th century, represents the culmination of Pythagorean cosmology and its transformation into modern science. Kepler explicitly identified himself as a Pythagorean and saw his astronomical work as fulfilling the Pythagorean project of discovering mathematical harmonies in celestial motions. His early work, Mysterium Cosmographicum, attempted to explain planetary distances through relationships among the 5 regular solids. His later masterwork, Harmonices Mundi, or Harmony of the World, sought musical ratios in the angular velocities of planets as viewed from the Sun. Kepler believed that God created the solar system according to mathematical harmonies, and that discovering these harmonies constituted genuine knowledge of divine creation. Kepler's harmonic astronomy differed from earlier versions in several crucial ways. It was based on precise observational data, particularly the observations of Tycho Brahe, rather than on a prioristic numerical speculation. It employed the heliocentric model with the Sun at the centre rather than the Philalaic system with its central fire. It recognized that planetary orbits are elliptical rather than circular. It involved complex calculations of angular velocities rather than simple assignments of musical notes. Yet despite these differences, Kepler's work represented a direct continuation of the Pythagorean project, understanding celestial phenomena through mathematics and finding in these mathematical relationships evidence of cosmic harmony and divine wisdom. The relationship between Pythagorean musical cosmology and modern science is complex. On the one hand, the specific doctrines about celestial tones, the central fire, the counter-earth, and simple assignments of musical intervals to planets have been abandoned as incompatible with physics and observational astronomy. Sound does not propagate through space. Celestial bodies do not move according to simple harmonic ratios. The cosmos is not organized as a musical scale. In this sense, Pythagorean cosmology was wrong and has been superseded. On the other hand, the fundamental Pythagorean insight that nature exhibits mathematical order and that understanding nature requires mathematical analysis has been vindicated spectacularly by modern science. Physics is formulated in mathematical language. The laws of nature are mathematical equations. Understanding phenomena means finding the mathematical structures they instantiate. Celestial mechanics, electromagnetism, quantum mechanics, relativity theory, all describe reality through mathematics. The Pythagorean vision that the book of nature is written in the language of mathematics, to use Galileo's phrase, has proven extraordinarily fruitful, even if specific Pythagorean astronomical theories were mistaken. The music of the spheres also endures as metaphor and aspiration. The idea that the cosmos exhibits harmony, that its parts are related in beautiful and intelligible ways, that studying nature reveals order and pattern, continues to motivate scientific inquiry. Physicists seek unified theories that would reveal deep symmetries and simple principles underlying diverse phenomena. The discovery of such unification, such as Maxwell's unification of electricity and magnetism, or the standard model of particle physics, evokes aesthetic responses analogous to appreciating musical harmony. Scientists speak of elegant theories, beautiful equations, symmetric structures, applying aesthetic language shaped by the Pythagorean tradition to mathematical physics. The Pythagorean doctrine of cosmic harmony also expressed metaphysical and ethical implications. If the cosmos is harmoniously ordered, then nature provides a model for human life and society. Human communities should seek to imitate cosmic order by establishing just and harmonious relationships among their members. Individual souls should strive for internal harmony analogous to the harmony of the spheres. Understanding cosmic order has ethical significance because it reveals the proper structure of reality to which human life should conform. This connection between cosmology and ethics, between how the universe is and how we should live, characterizes much ancient philosophy and reflects Pythagorean integration of natural philosophy with moral teaching. The historical origins of Pythagorean soul doctrine remain obscure. Some scholars trace it to influences from Egypt, where beliefs in the afterlife and the soul's journey were central to religious practice. Others point to possible connections with Indian philosophy and its doctrines of karma and reincarnation, though direct contact between early Greek and Indian thought is difficult to establish. Still others suggest that Pythagoras encountered these ideas in Persian or Zoroastrian contexts, or that he developed them independently from Greek mystery religions like Orphism, which also taught immortality and reincarnation. What seems clear is that Pythagorean soul doctrine represented a significant departure from the view of death and the afterlife found in Homer and mainstream Greek religion, which depicted the soul as a shadowy remnant surviving in Hades but lacking genuine life or personality. The Pythagorean teaching held that the soul is immortal and divine in nature. It does not perish with the body, but continues to exist, retaining memory, personality, and moral character. At death, the soul separates from the body and, after an interim period whose nature varied in different accounts, enters a new body to begin another life. The new incarnation may be as a human being, but it may also be as an animal, the particular form depending on the soul's condition and the quality of life led in the previous incarnation. A soul that has cultivated virtue and wisdom may be reborn in favourable circumstances or even escape the cycle of rebirth entirely. A soul steeped in vice and ignorance will be reborn in unfortunate conditions or in animal form as punishment and opportunity for purification. Pythagoras himself, according to ancient tradition, claimed to remember his previous incarnations. He reported having been Aethalides, a son of Hermes, then Euphorbus, a warrior in the Trojan War, then various other figures, before his current life as Pythagoras. In one famous anecdote, Pythagoras recognized the shield of Euphorbus hanging in a temple, identified it as his own from a previous life, and described details of Euphorbus's death at Troy. Whether these claims are historical or legendary, they illustrate the Pythagorean teaching that memory can sometimes bridge incarnations, that the soul retains traces of previous lives, and that spiritual adepts through purification and practice can recover these memories. The cycle of reincarnation was not viewed positively by the Pythagoreans. Unlike some religious traditions that celebrate the eternal return of the soul, Pythagoreanism regarded repeated incarnation as a burden, a form of imprisonment from which liberation should be sought. Each incarnation involves entanglement with matter, subjection to bodily desires and passions, forgetfulness of the soul's true nature, and further accumulation of moral debt. The goal of philosophy and the religious life was to purify the soul sufficiently to escape this cycle, to achieve a state where reincarnation was no longer necessary, where the soul could remain in a blessed condition free from material embodiment. This purification of the soul required multiple lifetimes of gradual progress. Through right action, philosophical study, ascetic discipline, and spiritual practice, the soul could shed moral impurity, overcome attachment to bodily existence, and remember its divine origin. The Pythagorean way of life, with its dietary restrictions, ethical teachings, mathematical studies, and communal practices, served this purificatory function. Every aspect of the Pythagorean discipline aimed at preparing the soul for its ultimate liberation. Philosophy was not merely intellectual inquiry, but a way of salvation, a systematic practice for achieving the soul's true good. The doctrine of metempsychosis had direct ethical implications, particularly regarding the treatment of animals. If the soul can transmigrate into animal bodies, then animals are potentially kin, perhaps literally relatives or friends from previous lives. To kill or eat animals is to risk harming beings who share our fundamental nature, who possess immortal souls like our own. This reasoning supported the Pythagorean practice of vegetarianism and prohibition on animal sacrifice. It established a radical ethical principle that all living beings deserve moral consideration, that the boundary between human and animal is less absolute than conventional morality assumes, that our obligations extend beyond the human community to embrace all ensouled creatures. This ethical stance was not purely sentimental or based on squeamishness about killing. It rested on serious metaphysical claims about the nature and destiny of souls. The Pythagoreans believed that cruelty to animals hardens the heart and perpetuates vice, making spiritual progress more difficult. They held that diet affects both body and soul, that consuming animal flesh promotes aggressive and passionate dispositions incompatible with philosophical contemplation. They taught that respecting the kinship of all life manifests understanding of reality's unity and the interconnection of all beings. These principles grounded vegetarianism in philosophical conviction rather than mere preference. Not all ancient sources agree on the details of Pythagorean dietary practice. Some texts suggest that certain animals were permitted for food while others were forbidden, or that animal sacrifice was acceptable under some circumstances. Some scholars argue that the strict vegetarianism attributed to Pythagoras may have been a later development, perhaps influenced by changing attitudes toward animal sacrifice in the Hellenistic period. Yet the association between Pythagoreanism and vegetarianism was strong throughout antiquity, and the ethical arguments based on metempsychosis were widely recognized as distinctively Pythagorean contributions to moral philosophy. The Pythagorean understanding of the soul involved both unity and complexity. On the one hand, the soul was regarded as a single immortal entity, the subject of experience and moral agency that persists through incarnations. On the other hand, later Pythagorean and Platonic psychology distinguished parts or aspects of the soul with different functions. Some accounts divided the soul into rational and irrational parts, with the rational part divine and immortal, while the irrational part perishes with the body. Other accounts distinguished among reasoning, emotion, and appetite as three parts or functions. These divisions attempted to explain psychological phenomena like internal conflict, where reason commands one action but desire impels another. Plato's Psychology in the Republic and Phaedo shows clear Pythagorean influence. He argues that the soul is immortal and survives bodily death, that it existed before birth and will exist after death, that it undergoes reincarnation depending on the life led, and that philosophy purifies the soul and prepares it for liberation. His tripartite division of the soul into reason, spirit, and appetite, with justice consisting in their proper harmony, applies Pythagorean concepts of proportion and harmony to psychology. His myth of air in the Republic, describing the soul's journey, Janvier 28. After death and its choice of new incarnation, presents Pythagorean doctrines in narrative form. Plato's modifications and developments of these ideas shaped subsequent Western philosophy's understanding of the soul. The Pythagorean doctrine of recollection or anamnesis held that learning is actually remembering what the soul knew before birth. Since the soul is immortal and has existed through many lives, it has encountered all kinds of things and learned truths about reality. Incarnation causes forgetfulness, but proper education can prompt the soul to remember these truths. When we grasp mathematical theorems or philosophical principles, we are not learning something entirely new, but recovering knowledge the soul once possessed. This doctrine has several philosophical attractions. It explains how we can know necessary truths that seem to exceed what experience teaches, it accounts for the apparent innateness of certain concepts and principles, and it provides epistemological support for rationalism over empiricism. Plato develops the doctrine of recollection in several dialogues, most famously in the Meno, where Socrates leads an untutored slave boy to prove a geometric theorem through questioning. The boy has never studied geometry, yet by reflecting on appropriate questions, he arrives at mathematical truth. Plato interprets this as showing that the soul already possessed this knowledge and needed only prompting to remember it. This Pythagorean Platonic epistemology influenced subsequent philosophy, appearing in modified forms in Augustine, Descartes, Leibniz, and other thinkers who emphasized innate ideas or rational insight over empirical learning. The Pythagorean view of the soul's relationship to the body was largely negative. The body was seen as a prison or tomb of the soul, using a pun in Greek. Soma, body, sounds like sema, tomb. Bodily existence binds the soul to material reality, subjects it to physical needs and pleasures, distracts it from intellectual and spiritual pursuits, and perpetuates its ignorance of divine truth. The ideal would be for the soul to exist free from bodily constraints, able to contemplate eternal realities without interference from sensation and desire. Since complete separation from body is possible only in death, and since death leads to reincarnation unless the soul is properly prepared, philosophy becomes a practice of dying, a gradual separation of soul from body achieved through ascetic discipline and contemplative practice. This body-soul dualism and its negative evaluation of embodiment had profound and controversial effects on Western thought. It encouraged ascetic practices, rejection of bodily pleasure, and suspicion of the material world. It supported otherworldly religious orientations focused on salvation after death rather than flourishing in this life. It sometimes led to denigration of the body, of sexuality, of ordinary human activities as hindrances to spiritual advancement. Later thinkers, including Aristotle and much of modern philosophy, have criticized this extreme dualism and its anti-Semitic implications, arguing for more integrated understandings of human nature where embodiment is essential rather than accidental to who we are. Yet the Pythagorean view also contained resources for more balanced perspectives. The soul required care and cultivation, but this could include appropriate attention to bodily health. The Pythagoreans practiced physical exercise, recognized the importance of proper diet and rest, and understood that a healthy body supports philosophical activity. Their musical practices engaged bodily experience through listening and performance. Their communal life involved embodied social relationships. Perhaps the body-soul dualism, while real, was not meant to deny value to embodied existence, but to prioritize the soul's ultimate good over temporary bodily satisfactions. The question of whether Pythagorean soul doctrine was meant literally or metaphorically presents interpretive challenges. Some modern scholars suggest that reincarnation teachings functioned symbolically, representing psychological transformations or ethical principles rather than actual transmigration of a substance soul into different bodies. The injunction to avoid eating beans, for example, might symbolize avoiding participation in democratic politics rather than literal dietary restriction. The soul's incarnation in animal form might represent degradation of character rather than literal metamorphosis. Yet ancient sources generally treat Pythagorean soul doctrine as literal belief, and the integration of these teachings with the rest of Pythagorean philosophy suggests they were meant seriously. The compatibility of Pythagorean soul doctrine with their mathematical philosophy raises interesting questions. Mathematics deals with eternal, unchanging truths, with abstract entities and necessary relationships. The soul, as an immortal entity capable of grasping these truths, must itself have something eternal and unchanging about it. Yet the soul also undergoes transformation, acquires and loses knowledge, suffers and flourishes through its incarnations. How can something be both eternal and changing, both divine and involved in material existence? These puzzles about the soul's nature parallel metaphysical puzzles about how abstract mathematical entities relate to concrete physical objects, about how the eternal manifests in time, about how unity gives rise to multiplicity. Pythagorean psychology influenced medical theory as well as philosophy. The idea that health consists in proper balance or harmony of elements parallels the psychological notion that well-being consists in proper ordering of the soul's parts. The recognition that psychological states affect physical health and vice versa reflects understanding of body-soul interaction. The therapeutic use of music to influence emotions and treat psychological disorders applies Pythagorean principles of harmony to healing practice. Later medical traditions, particularly those influenced by Hippocratic and Galenic medicine, incorporated these psychosomatic insights and holistic approaches to treating patients. The ethical teaching that we should cultivate virtue to purify the soul and improve our next incarnation introduced consequentialist reasoning into Greek ethics. Actions have consequences not just in this life, but across multiple lives. The soul carries accumulated moral qualities into future existences. This gives practical urgency to ethical cultivation. How we live now determines our fundamental well-being, not just temporarily, but perhaps eternally. The doctrine thus provided powerful motivation for moral seriousness and philosophical practice. If this life is merely one episode in the soul's long journey, and if that journey's direction depends on our choices, then nothing could be more important than getting life right. Pythagorean philosophy was never merely theoretical, but always integrated practical ethics and political engagement with metaphysical doctrine and mathematical study. The Pythagorean way of life, as we have seen, prescribed detailed rules of conduct, dietary restrictions, and spiritual practices. The Pythagorean community in southern Italy involved itself actively in civic affairs, with members occupying positions of political authority and influence. The ethical teachings of the school emphasized justice, friendship, self-examination, and the cultivation of virtue through disciplined practice. These practical dimensions of Pythagoreanism were inseparable from its theoretical commitments. The belief that reality is mathematically ordered implied that human life should exhibit similar order. The conviction that the soul is immortal and undergoes reincarnation gave urgency to ethical purification. The ideal of harmony discovered in music and cosmology extended to social relations and individual psychology. Yet the very success of the Pythagorean movement in gaining political power and social influence provoked opposition, leading to violent persecution that scattered the community and transformed Pythagoreanism from a unified school into a dispersed philosophical tradition. The Pythagorean conception of justice rested on mathematical foundations. Justice was understood fundamentally as a kind of equality or reciprocal proportion. In interpersonal relations, justice requires that exchanges be balanced, that each person receives equivalent to what they give. In distribution of goods or honours, justice requires that shares be proportionate to merit or contribution. In punishment, justice requires that penalty be proportionate to offence. This mathematical conception treated justice as a matter of correct ratio, of establishing proper numerical relationships among parts of a social whole. A society is just when its structure exhibits the right proportions, when each component performs its proper function and stands in appropriate relation to others. This idea of justice as proportion influenced Plato and Aristotle profoundly. Plato's Republic defines justice as each class in society doing its own work, with rulers ruling, auxiliaries defending, and producers producing in harmonious cooperation. Aristotle's detailed analysis of justice in the Nicomachean Ethics distinguishes distributive justice, which concerns proportionate allocation of goods, from corrective justice, which concerns restoring proper relations after injury. Both accounts reflect Pythagorean insight that justice involves proportion, balance, and mathematical structure. The ethical question, what is justice, becomes mathematizable. It concerns determining the right ratios and relationships. The Pythagoreans regarded friendship as the highest form of human relationship, and the model for ethical community. The famous saying attributed to Pythagoras, that friends hold all things in common, expressed both social ideal and metaphysical truth. True friends, having cultivated similarity of character through shared pursuit of wisdom and virtue, recognize their essential unity. What belongs to one belongs to the other. The good of one is inseparable from the good of the other. This perfect friendship transcends narrow self-interest and manifests the cosmic principle of unity underlying apparent plurality. The Pythagorean community attempted to realize this ideal through communal property, shared life, and bonds of loyalty among members. Friendship required honesty, trust, and mutual aid. Pythagoreans were expected to support one another in difficulty, to correct one another's errors, to maintain loyalty even at personal cost. Stories from ancient sources illustrate these ideals. One tells of two Pythagoreans, Damon and Phintius, where one stood as surety for the other's appearance before a tyrant willing to die if his friend failed to return. Another describes Pythagoreans travelling great distances to help a fellow member in need, even though they had never met personally. These stories, whether historical or legendary, express the ethical standards the community valued, that Pythagorean friendship involved absolute commitment, and that the bonds among members transcended ordinary social relationships. This emphasis on friendship as philosophical ideal raises questions about exclusivity and boundaries. If perfect friendship requires similarity of character and shared commitment to philosophy, what about relationships with non-philosophers? The Pythagorean distinction between members and outsiders, between those initiated into the teachings and those excluded, created an ethical asymmetry. Full moral obligations applied primarily within the community, though basic duties of non-harm and justice extended to all. This tension between universal ethical principles and special obligations to fellow community members would recur in various forms throughout ethical thought, from Stoic cosmopolitanism to Christian universalism, to modern debates about partiality and impartiality in ethics. The practice of self-examination, as described earlier, served ethical development by cultivating moral awareness and intentionality. The threefold evening review asking, "What have I done wrong? What have I accomplished? What duties have I left unfulfilled?" trained practitioners to monitor their conduct, recognize failures, and resolve to improve. This technique presumed that virtue results from habituation, from repeated practice of right action, from conscious effort to align behavior with rational principles. One does not become virtuous simply by understanding what virtue is, but by actually acting virtuously repeatedly until good conduct becomes second nature. This emphasis on habituation and practice connects to the Pythagorean understanding of education as transformation rather than mere information transmission. Education aims not just to impart knowledge, but to shape character, to cultivate dispositions and capacities, to prepare the student for philosophical and ethical life. The lengthy probationary period, the period of silence, the graduated initiation into deeper teachings all reflected recognition that moral and intellectual transformation takes time and requires appropriate conditions. One cannot simply tell someone the truth and expect them to grasp it immediately. Rather, the person must be prepared gradually through discipline and practice. The political involvement of Pythagoreans in southern Italian cities brought the school into conflict with democratic factions and rival aristocratic groups. The Pythagoreans generally supported oligarchic government ruled by a virtuous and educated elite rather than by the mass of citizens. This political stance reflected their philosophical commitments. Since wisdom and virtue require long cultivation through education and practice, and since most people lack opportunity or inclination for such cultivation, governance should be entrusted to those who have achieved philosophical understanding. Democracy, by giving equal political power to all regardless of virtue or knowledge, seemed to the Pythagoreans to abandon reason for opinion, to make emotion rather than wisdom the basis of political decisions. This anti-democratic stance made Pythagoreans unpopular with common citizens and vulnerable to populist opposition. In cities where Pythagoreans held power or influence, resentment built among those excluded from political participation or disadvantaged by Pythagorean policies. Around 500 BCE, according to ancient sources, this resentment erupted in violent attacks. In Croton and other cities, meeting houses where Pythagoreans gathered were burned, members were killed or forced to flee, and the organised communities were destroyed. The details vary in different accounts, but all agree that organised Pythagoreanism in southern Italy suffered catastrophic suppression in the late 6th or early 5th century. The causes of this persecution were political, social, and perhaps economic rather than purely philosophical. The Pythagorean movement represented a powerful faction that ordinary citizens viewed as threatening. Their secrecy bred suspicion. Their claims to superior wisdom seemed arrogant. Their communal solidarity appeared as conspiracy. Their political dominance excluded others from power. The violence that destroyed the communities thus reflected class conflict, democratic resistance to oligarchy, and resentment of an intellectual elite as much as any specific opposition to Pythagorean doctrines. Yet the persecution may also have had religious dimensions. The Pythagorean way of life, with its distinctive practices and doctrines, diverged significantly from traditional Greek religion. Their vegetarianism and opposition to animal sacrifice challenged conventional religious ritual. Their secret teachings and initiation practices resembled mystery cults and may have been viewed with suspicion by civic authorities. Their claims about metempsychosis and the soul's nature contradicted mainstream beliefs. While ancient sources do not emphasize religious persecution as such, the religious distinctiveness of Pythagoreanism likely contributed to broader social hostility. The aftermath of the persecution saw the dispersion of Pythagorean teaching and its transformation from a unified school centered on a living master to a diverse tradition maintained by scattered followers. Surviving Pythagoreans fled to other cities, particularly to mainland Greece. Some, like Philolaus and Archytas, continued philosophical work and teaching, developing Pythagorean ideas in new contexts. Others preserved Pythagorean ethical and religious practices while perhaps de-emphasizing mathematical philosophy. The tradition fragmented, with different groups maintaining different aspects of Pythagorean teaching and disagreeing about what was most essential. This dispersion had significant intellectual consequences. It brought Pythagorean ideas into contact with other philosophical schools. Pythagorean influence on Plato occurred in this context of dispersed teaching rather than organized school. Plato encountered Pythagorean thinkers in southern Italy and Sicily and incorporated their mathematical philosophy into his own system. The Academy in Athens, which Plato founded and which became the leading philosophical school of the 4th century, transmitted Pythagorean ideas even while developing them in new directions. Aristotle's detailed discussions of Pythagorean doctrines in his Metaphysics preserve information about the school while also subjecting its claims to critical analysis. The later history of Pythagoreanism involves cycles of revival and adaptation. In the Hellenistic period, Neo-Pythagorean movements emerged, claiming to restore authentic Pythagorean teaching. These movements emphasized religious and mystical elements, treating Pythagoras as a divine figure and collecting miracles and legends about him. The Lives of Pythagoras by Porphyry and Iamblichus, written in late antiquity, present Pythagoras as sage, miracle worker, and moral exemplar rather than primarily as mathematician or philosopher. This Neo-Pythagoreanism influenced Neoplatonism and through it late ancient philosophy generally. In evaluating Pythagorean political philosophy and the persecution that ended organized Pythagoreanism, we confront difficult questions about the relationship between philosophical conviction and political practice, between intellectual elitism and democratic participation, between the ideal of rule by wisdom and the dangers of oligarchic oppression. The Pythagorean position that governance requires philosophical understanding and that not all are capable of such understanding has both serious arguments supporting it and troubling implications. Modern democracies struggle with related tensions between expertise and popular sovereignty, between technocratic governance and democratic accountability. The Pythagorean ideal of a philosophical community dedicated to wisdom and virtue, living according to rational principles and cultivating excellence, remains attractive to many. Yet the historical reality of such communities often involves exclusivity, hierarchy, and potential for abuse of power. The tension between philosophical ideals and political realities, between theoretical commitments to justice and harmony and actual conduct in circumstances of conflict and opposition, affects not just Pythagoreanism, but any attempt to organize society according to philosophical principles. The violent end of organized Pythagoreanism reminds us that philosophy does not operate in a social vacuum. Philosophical schools exist within political contexts, interact with broader social forces, and face practical consequences of their teachings and practices. The Pythagorean attempt to implement their vision of rational social order through political power ended in catastrophe. Yet the philosophical ideas, freed from organizational structure and political ambition, proved remarkably durable. They influenced subsequent thought, inspired later thinkers, and contributed to enduring conversations about mathematics, metaphysics, ethics, and the nature of reality. Perhaps this constitutes a kind of vindication, that philosophical truth survives political defeat, that ideas prove more powerful than institutions, that thought transcends the circumstances of its origin. The influence of Pythagorean philosophy on subsequent Western thought is both profound and pervasive, extending from ancient philosophy through medieval cosmology to Renaissance humanism and modern mathematics and science. Pythagorean ideas about mathematics, harmony, the soul, and cosmic order shaped Plato, and through him the entire Platonic tradition. The Pythagorean vision of reality as fundamentally mathematical established a paradigm for natural philosophy that achieved its fullest realization in modern physics. Pythagorean ethical teachings influenced Stoicism and later moral philosophy. Pythagorean cosmology, particularly the doctrine of the music of the spheres, inspired astronomical investigation and poetic imagination across 2 millennia. Even where specific Pythagorean doctrines were rejected or superseded, the questions they raised and the approaches they pioneered continued to shape philosophical and scientific inquiry. To trace the legacy of Pythagoreanism is to follow one of the major streams of Western intellectual history, to see how ancient insights were preserved, transformed, and adapted across diverse cultural and intellectual contexts. Plato represents the most important single channel through which Pythagorean philosophy influenced later thought. Plato encountered Pythagorean thinkers during his travels in southern Italy and Sicily, including Archytas of Tarentum, a leading Pythagorean mathematician and statesman. These encounters profoundly affected Plato's philosophical development, particularly his views about mathematics, the soul, and the structure of reality. The Republic, Plato's masterwork of political philosophy, shows Pythagorean influence in its emphasis on mathematical education as preparation for philosophy, its conception of justice as harmony among parts of the soul and city, its doctrine that philosophers should rule because they possess knowledge of eternal truths, and its use of mathematical analogies to explain philosophical concepts. The Timaeus, Plato's cosmological dialogue, presents a comprehensive vision of the cosmos clearly indebted to Pythagorean ideas. The dialogue describes the creation of the world by a divine craftsman who shapes matter according to eternal mathematical forms. The world soul, which animates the cosmos and produces celestial motions, is constructed according to musical ratios. The four elements, earth, water, air, and fire, are analyzed into geometric solids composed of triangles. The entire cosmos exhibits mathematical structure and harmonic proportions. While Plato develops these ideas in his own distinctive way, incorporating his theory of forms and other characteristic doctrines, the underlying vision of reality as mathematically ordered derives from Pythagoreanism. Plato's theory of forms, though it differs significantly from Pythagorean number philosophy, shares crucial assumptions with Pythagoreanism. Both hold that reality divides into two realms: eternal, unchanging, intelligible entities grasped by reason, and temporal, changing, sensible objects known through perception. Both regard the eternal realm as more real and more valuable than the temporal realm. Both hold that understanding consists in grasping eternal truths through rational insight rather than in accumulating empirical observations. Both see philosophy as a practice that purifies the soul and prepares it for contemplation of eternal realities. These fundamental metaphysical and epistemological commitments, shared by Pythagoreanism and Platonism, shaped Western philosophy for 2,000 years. The Platonic Academy, which continued for centuries after Plato's death, maintained strong emphasis on mathematics. The inscription over the Academy's entrance allegedly read, "Let no one ignorant of geometry enter," reflecting the Pythagorean Platonic conviction that mathematical knowledge is prerequisite for philosophy. Academic philosophers investigated mathematics intensively, producing results in geometry, arithmetic, and astronomy. They debated the ontological status of mathematical entities, their relationship to physical objects, and their role in cosmology. This mathematical tradition within Platonism ensured that Pythagorean ideas remained central to ancient philosophy. Aristotle, though critical of specific Pythagorean doctrines, engaged seriously with Pythagorean philosophy throughout his works. His Metaphysics contains extensive discussion of Pythagorean number philosophy, analyzing its claims, identifying its strengths and weaknesses, and attempting to distinguish legitimate insights from confused metaphysics. Aristotle's own philosophy, while rejecting Pythagorean Platonic dualism in favor of hylomorphism, retains the Pythagorean emphasis on form, structure, and mathematical intelligibility in nature. His scientific works, particularly in biology and physics, employ concepts of proportion, balance, and harmony clearly influenced by Pythagorean thinking. The Stoic school, founded in the generation after Aristotle, absorbed Pythagorean ethical teachings, particularly the practice of self-examination and the ideal of living according to reason. The Stoic conception of the cosmos as a rational, providentially ordered whole reflects Pythagorean cosmology. The Stoic emphasis on mathematics as revealing cosmic structure, and the Stoic doctrine that virtue consists in proper proportion and harmony of the soul's faculties show Pythagorean influence. Later Stoics like Seneca and Marcus Aurelius incorporated the Pythagorean practice of evening review into their ethical discipline, making it a standard exercise in Stoic spiritual training. Neoplatonism, the dominant philosophical movement of late antiquity, revived an intensified interest in Pythagorean philosophy. Plotinus, the founder of Neoplatonism, drew heavily on both Plato and Pythagoras in constructing his metaphysical system. His doctrine of emanation from the one to intellect to soul to material world employs Pythagorean numerical symbolism and concepts of mathematical generation. His student Porphyry wrote a Life of Pythagoras that presented the ancient sage as the perfect philosopher and moral exemplar. Iamblichus, another major Neoplatonist, wrote an even more elaborate Life of Pythagoras and works on Pythagorean number theory, treating Pythagoreanism as a complete philosophical and religious system. The Neoplatonic revival of Pythagoreanism emphasized its religious and mystical dimensions, treating Pythagoras as a divine figure whose teachings offered a path to salvation. This religious Pythagoreanism influenced late pagan thought and competed with Christianity for spiritual allegiance in the declining Roman Empire. When Christianity became dominant, some Christian thinkers incorporated Pythagorean Neoplatonic ideas into Christian theology. Augustine, though critical of pagan philosophy in many respects, accepted Platonic Pythagorean doctrines about the soul's immortality and the primacy of eternal truths over temporal things. The integration of Platonic philosophy with Christian theology in Augustine and later medieval thinkers ensured that Pythagorean ideas, transmitted through Platonic channels, remained influential. Medieval philosophy and science inherited Pythagorean ideas primarily through three sources: Platonic dialogues, particularly the Timaeus; Aristotle's works, which discussed Pythagorean doctrines critically; and late ancient encyclopedic works like Boethius, De Institutione Arithmetica and De Institutione Musica, which transmitted Pythagorean mathematical and musical theory. These sources shaped medieval cosmology, music theory, and the educational curriculum. The quadrivium, the four mathematical sciences of arithmetic, geometry, astronomy, and music, had Pythagorean roots and reflected Pythagorean ideals of mathematical education as foundation for wisdom. Medieval cosmology, as expressed in Dante's Divine Comedy and in scholastic philosophy, incorporated the Pythagorean vision of a harmoniously ordered cosmos structured by mathematical principles. The celestial spheres, carrying planets and stars in their revolutions, produced cosmic harmony. The material world reflected eternal mathematical patterns. Understanding creation meant grasping the numerical relationships through which God ordered reality. This Christianized Pythagoreanism provided a framework for integrating Aristotelian natural philosophy with biblical revelation and Platonic metaphysics. The Renaissance brought renewed interest in ancient philosophy and a revival of Pythagorean ideas in relatively pure form. Marsilio Ficino's translations of Plato and Plotinus made these texts widely available to European intellectuals. Renaissance humanists sought ancient wisdom in Pythagorean number symbolism and mysticism. Artists and architects incorporated ideas about mathematical proportion and harmonic relationships into their work. Natural philosophers sought to discover mathematical harmonies in nature, reviving the Pythagorean project of understanding the cosmos through number. Johannes Kepler represents the culmination of Renaissance Pythagoreanism and its transformation into modern science. Kepler explicitly identified as a Pythagorean and regarded his astronomical work as discovering the mathematical harmonies God had built into creation. His laws of planetary motion, which describe the elliptical orbits of planets and relate orbital periods to distances from the Sun through precise mathematical relationships, vindicated the Pythagorean conviction that celestial phenomena obey mathematical laws. Though his specific attempts to find musical ratios in planetary motions and to explain distances through the 5 regular solids were not successful, his methodological commitment to mathematical explanation proved extraordinarily fruitful. Galileo's famous assertion that the book of nature is written in the language of mathematics, that only through geometry and number can natural phenomena be understood, directly echoes Pythagorean doctrine. Galileo's mathematical approach to physics, analyzing motion through geometric relationships and quantitative laws, established the paradigm for classical mechanics. Newton's Principia Mathematica, which unified terrestrial and celestial mechanics through universal mathematical laws, achieved what the Pythagoreans had envisioned: a comprehensive mathematical account of natural phenomena revealing the rational structure of the cosmos. Modern mathematics and physics have vindicated the Pythagorean vision more completely than the Pythagoreans themselves could have imagined. All fundamental physical theories are formulated mathematically. Quantum mechanics describes reality through abstract mathematical structures whose relationship to everyday experience is highly indirect. Relativity theory explains space, time, and gravitation through differential geometry. Particle physics employs sophisticated mathematical frameworks involving symmetry groups and quantum field theories. The entire project of modern physics consists in finding mathematical patterns in nature, in formulating quantitative laws, in revealing the mathematical structure that underlies and explains physical phenomena. This success of mathematical physics raises philosophical questions the Pythagoreans first confronted. Why is mathematics so effective in describing nature? Is this because reality is fundamentally mathematical, or because mathematics is simply an extremely useful tool? Do mathematical entities exist independently of human minds, or are they human constructions? What is the relationship between abstract mathematical theories and concrete physical reality? These questions, debated in contemporary philosophy of mathematics and philosophy of science, continue conversations begun by the Pythagorean school over 2 millennia ago. The Pythagorean emphasis on mathematical proof and deductive reasoning shaped the development of mathematics as a discipline. Euclid's Elements, the foundational text of geometry for 2,000 years, exemplifies Pythagorean ideals of systematic organization and rigorous demonstration. The axiomatic method, which Euclid employed and which has become standard in mathematics, originates with Pythagorean requirements for proof. Modern mathematics retains this structure: definitions of basic concepts, axioms taken as starting points, theorems derived through logical deduction. The Pythagorean conviction that mathematical knowledge is certain, established through proof rather than observation, remains central to mathematical practice. The discovery of non-Euclidean geometries in the 19th century and the development of alternative foundations for mathematics in the 20th century raised questions about the certainty and uniqueness of mathematical truth. If multiple consistent geometric systems exist, which one describes actual space? If different axiom systems for arithmetic or set theory are possible, which is correct? These questions echo the Pythagorean crisis over irrational numbers, which showed that reality is mathematically richer than initially assumed. They suggest that the relationship between mathematics and reality remains philosophically puzzling despite the enormous success of mathematical science. Pythagorean aesthetics, the idea that beauty consists in mathematical proportion and harmony, has influenced Western art and music throughout its history. Renaissance artists studied mathematical perspective and proportional relationships. Baroque composers explored mathematical structures in fugues and canons. Modernist artists investigated geometric abstraction. Contemporary music theory continues to analyze harmonic relationships mathematically. While the specific claim that beauty reduces to simple numerical ratios has been rejected as too narrow, the broader idea that mathematical structure contributes to aesthetic value remains influential. Pythagorean ethical teachings about self-examination, the philosophical life, and moral cultivation have echoed through Western philosophy. The Socratic examined life, the Stoic practice of reviewing each day, the Christian examination of conscience, secular practices of journaling and self-reflection all trace back to Pythagorean origins. The ideal of philosophy as a way of life, not just academic study but comprehensive practice aimed at wisdom and virtue, periodically resurfaces against tendencies to reduce philosophy to technical analysis. The Pythagorean integration of intellectual inquiry with moral transformation remains an attractive vision, even as modern philosophy has largely professionalized and specialized. The Pythagorean doctrine of the soul's immortality and transmigration influenced Western religious thought, though usually in modified forms. Christian theology rejected reincarnation, but accepted the soul's immortality and its ultimate destiny as determined by earthly conduct. The soul's purification through earthly trial, its journey toward divine wisdom, its potential liberation from material constraints, these themes in Christian spirituality have Pythagorean Platonic roots. The tension between otherworldly and this worldly orientations, between valuing embodied life and seeking transcendence, reflects unresolved issues in Pythagorean philosophy about the soul's relationship to the body and material existence. Modern interpretations of Pythagoreanism vary widely. Some scholars emphasize its mathematical achievements and its contribution to the foundations of science. Others stress its religious and mystical dimensions as a comprehensive worldview, uniting reason and revelation. Still others focus on its ethical teachings and its vision of philosophical community. These different interpretations reflect genuine tensions and complexities within Pythagorean thought itself, which unified diverse elements, mathematics and mysticism, rational inquiry and religious devotion, systematic philosophy and esoteric teaching into a single comprehensive tradition. The enduring fascination with Pythagoreanism reflects its address to perennial human concerns. The search for underlying unity and order in apparently diverse and chaotic phenomena, the conviction that reality is intelligible to human understanding, the aspiration to find beauty and meaning in mathematical structure, the hope that knowledge brings ethical insight and spiritual fulfillment, these Pythagorean themes resonate across cultures and centuries. Whether we accept specific Pythagorean doctrines or not, the questions they raised about the nature of reality, the power of mathematics, the destiny of the soul, and the good life remain philosophically vital. As we conclude this exploration of Pythagorean philosophy, we recognize both its historical importance and its continuing relevance. The Pythagorean school initiated inquiries that shaped Western philosophy, established methods that grounded mathematical science, and proposed visions of cosmos and soul that influenced religious thought. Their bold claim that all is number, however we interpret it, expressed conviction that reality exhibits rational structure, that human beings can grasp this structure through disciplined inquiry, and that understanding reality has practical and spiritual significance. This conviction, refined and developed across centuries, underlies much of modern science and continues to motivate philosophical reflection. The integration of diverse domains, mathematics and music, astronomy and ethics, cosmology and spiritual practice that characterized Pythagorean philosophy seems increasingly difficult in our era of disciplinary specialization. Yet the aspiration to comprehensive understanding, to seeing connections among apparently separate fields, to finding unity in diversity, remains philosophically important. The Pythagoreans remind us that philosophy, at its best, seeks not just technical mastery of specialized questions, but wisdom about fundamental matters, insight into the structure of reality and the nature of the good life. Whether we work within the Pythagorean tradition or stand outside it, engaging seriously with Pythagorean thought enriches our understanding of philosophy's possibilities and deepens our appreciation for the perennial human quest to comprehend ourselves and our place in the cosmos.